Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin our journey into the mysterious regions above and below our solar system, take a moment to get comfortable. Let your body settle into whatever soft place you've chosen for tonight. Where in the world are you watching from? Perhaps you're in a quiet bedroom with the lights dimmed low, or maybe you're in a cozy corner where the day is finally releasing its hold on you. Wherever you are, you're exactly where you need to be. Tonight we're going to explore something truly remarkable, yet strangely overlooked. We're going to drift slowly through the vast regions that exist above and below the flat plane of our solar system. We'll discover what fills those seemingly empty spaces, understand why our solar system is shaped like a disk in the first place, and contemplate the strange objects and forces that occupy the vertical dimensions of our cosmic neighbourhood. It's a journey that spans billions of kilometres, from the Kuiper Belt's gentle arc to the mysterious Oort Cloud that surrounds everything we know. But don't worry, this isn't going to be a frantic race through space facts or a breathless countdown of cosmic dangers. Instead, we'll move slowly and carefully through these overlooked dimensions, taking our time with each discovery, pausing to appreciate the gentle strangeness of it all. By the end, I think you'll find yourself looking at the night sky differently, understanding that our solar system isn't just spread out horizontally, but extends vertically into regions few people ever think about. If you enjoy these calm explorations of space, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with your final thoughts before sleep, so settle in. Let your shoulders drop away from your ears, take a slow breath, hold it gently, and release. And let's begin our slow drift through the space above and below our solar system. There's nowhere you need to be right now. Nothing you need to remember or accomplish. Just listen, and let the story of these vertical reaches unfold around you, like a gentle blanket of stars. Before we can understand what exists above and below our solar system, we need to contemplate something we often take for granted: why our solar system is shaped like a disk in the first place. It's one of those facts that seems obvious once you see pictures of it. All the planets lined up in roughly the same flat plane, but the reason behind this shape is actually quite beautiful. Imagine, if you will, going back 4.5 billion years to a time when our solar system didn't exist yet. Where our sun now burns, there was only a vast cloud of gas and dust, floating in the darkness between older stars. This cloud was enormous, perhaps several light years across, and it was rotating ever so slowly. The rotation itself came from the general motion of matter in our galaxy, a gentle spin inherited from the cosmic environment. Now, here's where the beauty begins. As this cloud began to collapse under its own gravity, pulled inward by the mutual attraction of all its countless particles, something wonderful happened. The rotation sped up. Think of an ice skater pulling their arms in during a spin, moving faster and faster. The cloud did the same thing, spinning more rapidly as it contracted, and as it spun, it began to flatten. This flattening wasn't random. It was the inevitable result of physics playing out on a grand scale. Material that was moving perpendicular to the rotation, trying to go up or down, would collide with other material. These collisions would average out those vertical motions, converting that energy into heat and spreading it away. But the rotational motion, the sideways movement, had nowhere to go. It was conserved, preserved, building up as the cloud spun faster, over millions of years. The cloud transformed from a roughly spherical blob into a flat rotating disk. At the centre, where most of the mass concentrated, the pressure and temperature climbed until nuclear fusion ignited and our sun was born. But surrounding this newborn star was a vast disk of leftover material, the protoplanetary disk from which everything else would form. The planets, asteroids, and most other objects in our solar system formed from this disk. and that's why they all orbit in roughly the same plane even today. They're like fossils of that ancient flattening process, still following the paths laid down billions of years ago. When we look at images of the solar system from the side, seeing all the planets strung out in a line, we're seeing the echo of that original disk. But here's what makes our exploration tonight interesting. While most of the mass ended up in this flat disk, and while most objects follow paths close to this plane, the solar system doesn't end at the disk's edge. Above and below this familiar territory, space stretches outward in dimensions that are rarely discussed, rarely imagined, yet just as real as the ecliptic plane we know so well. And it's to these overlooked regions that we now turn our attention. When we talk about what's above and below the solar system, we first need to understand what we mean by those directions. In space, of course, there's no absolute up or down. These terms only make sense relative to something else. For our purposes, we'll define quote 0 and quote 1 as the directions perpendicular to the ecliptic plane, which is the flat plane that contains Earth's orbit around the Sun. Imagine the ecliptic as a vast invisible sheet stretching across space. Most of the planets orbit within a few degrees of this sheet. Mercury, the most inclined, tilts only about 7 degrees from it. The others are even closer to the plane. But if we travel perpendicular to this sheet, heading straight up or straight down, we can measure the vertical extent of our solar system's various regions. The first boundary we might consider is the Kuiper Belt, that region beyond Neptune where countless icy bodies orbit. The Kuiper Belt itself is relatively flat, most objects staying within 10 or 15 degrees of the ecliptic. But even this slight angle means that at the belt's outer edge, some 40 to 50 astronomical units from the Sun, objects can be several astronomical units above or below the main plane. An astronomical unit, remember, is the distance from Earth to the Sun, about 150 million kilometres. So even this relatively flat region has a vertical thickness of hundreds of millions of kilometres. Then there are the scattered disk objects, bodies whose orbits were perturbed by gravitational interactions with Neptune and other planets. These follow much more elongated and tilted paths, some reach inclinations of 30, 40, even 60 degrees or more. At their farthest points from the Sun, hundreds of astronomical units away, these orbits can take objects tens of astronomical units above or below the ecliptic plane. We're talking about vertical distances that dwarf the diameter of Neptune's orbit. But the true vertical extent of the solar system becomes apparent when we consider the Oort Cloud. This theoretical sphere of icy bodies is thought to surround the entire solar system at distances of thousands or even tens of thousands of astronomical units. Unlike the disk-like inner solar system, the Oort Cloud is believed to be roughly spherical, extending equally in all directions from the Sun, up, down, and sideways. If the Oort Cloud extends to 50,000 astronomical units, as some models suggest, then objects could exist 50,000 astronomical units above the ecliptic plane. That's nearly 1 light-year of vertical distance. To put that in perspective, it would take light, moving at 300,000 kilometers per second, almost a full year to travel from the ecliptic plane to the top of the Oort Cloud. These distances are so vast they're almost meaningless without context, but perhaps it helps to think of it this way. If you built a model where the Sun was the size of a basketball, the Earth would be a grain of sand about 26 meters away. Neptune would be another grain of sand about 800 meters away. But the Oort Cloud, in this model it would extend for about 22 kilometers in every direction, up, down, and sideways. The vertical dimension of our solar system is truly immense. What fills these vast vertical reaches? What strange objects drift through these regions that humans rarely imagine? Let's contemplate that question slowly as we continue our gentle exploration. Every now and then something remarkable happens. A comet appears in our skies, having fallen from the heights or depths above and below our solar system, plunging down toward the Sun in a dramatic, elongated orbit. These visitors from the vertical dimensions give us our most tangible connection to the space beyond the ecliptic plane. Consider a comet like Hale-Bopp, which graced our skies in 1997. Its orbit was inclined about 89 degrees to the ecliptic, meaning it was travelling almost perpendicular to the plane of the planets. It didn't swing around the Sun in the same direction as Earth and the other planets. Instead, it plunged down from high above the solar system, swung past the Sun, and then climbed back up again on the other side like a needle threading through fabric. Where did Hale-Bopp come from? Most likely the Oort Cloud, that vast spherical shell of icy bodies we mentioned earlier. The Oort Cloud comets can approach the Sun from any direction, from directly above the ecliptic, from directly below, or from any angle in between. This is one of the key differences between Oort Cloud comets and those from the Kuiper Belt. Kuiper Belt comets tend to stay relatively close to the ecliptic plane because that's where the Kuiper Belt itself resides. But Oort Cloud comets show no such preference. They come from all directions equally. What's fascinating is that these comets spent billions of years in the quiet, cold darkness above or below the plane of the planets, so far from the Sun that its warmth was barely distinguishable from other stars. They orbited out there in the deep freeze, unchanged since the solar system's formation, preserving pristine samples of the original material from which everything formed. Then something happened. Perhaps a passing star's gravity tugged gently on the distant comet. Perhaps the gravitational influence of the galaxy's tidal forces shifted its orbit just enough. Whatever the cause, the comet's path changed slightly, and it began the long fall inward. Over thousands or millions of years, it dropped down through the vertical dimensions of the solar system, accelerating as the Sun's gravity pulled it closer. By the time it reached the inner solar system where Earth orbits, the comet was moving incredibly fast, tens of kilometers per second. The Sun's heat began to vaporize its ices, creating the magnificent tail that made it visible to humans far below. We watched it for months as it swung past the Sun and began the long climb back upward, back to the cold heights from which it came. Some comets, like Hale-Bopp, have orbits so elongated that they'll take thousands of years to return. Others have been perturbed by planetary gravitational interactions into shorter orbits, becoming the periodic comets we see more frequently. But in either case, these icy visitors are our messengers from the vertical reaches of the solar system. Rare glimpses of what exists in the spaces we cannot easily explore. What's particularly moving is that some comets come from so far above or below the plane that they've likely never been in the inner solar system before. Their current visit is their first in 4.5 billion years. They formed out there in the heights or depths, and they're only now, in the present era, making their maiden voyage past the Sun. We're witnessing their first and perhaps only journey through the realm of the planets. And when they depart, climbing back up or sinking back down into the vertical dimensions beyond the planets, they carry with them a tiny change. The Sun's heat has altered them, boiling away some of their ice, perhaps splitting them into fragments. They return to the heights or depths marked by their brief encounter with warmth and light, forever changed by their fall through our world. We've established that the solar system is primarily disk-shaped, but it's worth contemplating why that disk wasn't perfect, why there are objects in the vertical dimensions at all. The story of this imperfection is actually a story about chaos and violence in the early solar system, about gravitational interactions that scattered objects in all directions. When the planets were forming, the solar system was a much more chaotic place than it is today. The disk of material around the young Sun was thick with planetesimals, kilometre-sized chunks of rock and ice that were slowly colliding and merging to build larger bodies. This process wasn't gentle or orderly. It was violent and random. As the gas giant planets, Jupiter, Saturn, Uranus, and Neptune grew massive enough to gravitationally dominate their regions, they began to interact with the remaining planetesimals. These interactions were transformative. A small, icy body passing close to Jupiter might receive a gravitational kick that completely changed its orbit. An object previously travelling in a nice circular path in the ecliptic plane might be flung into an elongated orbit that took it far above or below the plane. The process was called scattering, and it was enormously effective at clearing the planetary regions of leftover debris. Jupiter and Saturn in particular were like cosmic vacuum cleaners, though they didn't capture most of the material. Instead, they threw it away, flinging planetesimals into the outer solar system, or sometimes ejecting them from the solar system entirely. Many of these scattered objects ended up in highly inclined orbits. An object given a gravitational kick at just the right angle might find itself on a path tilted 30, 40, or even 90 degrees to the ecliptic, and once in such an orbit there was nothing to flatten it back down. In the outer solar system, there wasn't enough material left for collisions to average out the vertical motions like they had in the original disk. This scattering process is thought to have populated the scattered disk, that region beyond Neptune where objects follow highly elongated and inclined orbits. It may have also populated parts of the Oort Cloud, though the Oort Cloud's formation is still debated. Some models suggest that many Oort Cloud objects were originally formed much closer to the Sun, in the region where the giant planets now reside, and were scattered outward by those same planets' gravity. What's particularly interesting is that this scattering wasn't a one-time event. It's a process that continued over millions of years and in some ways continues even today, though at a much slower rate. The solar system is still, very gradually evolving, still clearing out the last remnants of its formation. There's also the influence of passing stars to consider. Our Sun isn't isolated in space. It's part of the Milky Way galaxy, orbiting the galactic centre along with hundreds of billions of other stars. Occasionally, over billions of years, another star passes relatively close to our solar system. When this happens, that star's gravity can perturb the orbits of distant objects, especially those in the Oort Cloud. These stellar encounters can shift orbits, increasing or decreasing their inclinations, changing their orientations. They can take an object that was orbiting roughly in the ecliptic plane and tilt it into a more vertical orbit, or vice versa. They can also send objects from the outer Oort Cloud falling inward toward the Sun, contributing to the population of comets we occasionally see. Then there's the galaxy's own tidal force. The Milky Way isn't uniform, it has more mass in some directions than others, particularly toward the galactic centre. This uneven distribution creates a tidal force, a gravitational gradient that can torque the orbits of the most distant solar system objects. This galactic tide is thought to be one of the mechanisms that sends Oort Cloud comets falling inward. All these processes mean that the vertical distribution of objects in our solar system is dynamic, slowly changing over time. The solar system isn't a static disk with a static sphere around it. It's an evolving system, its structure shaped by billions of years of gravitational interactions, both internal and external. The objects above and below the ecliptic plane carry this history in their orbits, each one a record of ancient encounters and perturbations. Let's turn our attention now to the Kuiper Belt, that region beyond Neptune where countless icy bodies orbit in the dimness. While the Kuiper Belt is often described as extending roughly in the plane of the ecliptic, its vertical structure is more interesting than most people realise. The Kuiper Belt begins at about 30 astronomical units from the Sun, just beyond Neptune's orbit, and extends outward to roughly 50 astronomical units. Within this region, there are estimated to be hundreds of thousands of objects larger than 100 kilometres across, and millions of smaller ones. The most famous resident is Pluto, but Pluto is just one of many large Kuiper Belt objects. Most Kuiper Belt objects orbit within about 10 degrees of the ecliptic plane. This means that at the belt's outer edge, at 50 astronomical units, the vertical spread is roughly 8 or 9 astronomical units. That's more than the distance from the Sun to Saturn. So while the Kuiper Belt is relatively flat compared to the Oort Cloud, it still has substantial vertical thickness. But within the Kuiper Belt there's structure. Some regions are more densely populated than others. Some orbital resonances with Neptune concentrate objects into specific paths, and interestingly, the inclination distribution isn't random. There are populations of Kuiper Belt objects with different inclination patterns, reflecting different formation and evolutionary histories. The classical Kuiper Belt objects, those in relatively circular orbits that never come close to Neptune, typically have lower inclinations. They mostly stay within a few degrees of the ecliptic. These are thought to be the least disturbed objects, bodies that formed roughly where they are now and haven't been significantly perturbed since. But then there are the scattered disk objects and the detached objects, bodies with more eccentric and inclined orbits. Some of these reach inclinations of 40 degrees or more. At their most distant points, hundreds of astronomical units from the Sun. They can be tens of astronomical units above or below the ecliptic plane. One particularly intriguing example is Sedna, discovered in 2003. Sedna's orbit is extraordinarily elongated, taking it from about 76 astronomical units at its closest approach to the Sun out to nearly 1,000 astronomical units at its farthest. Its orbit is also inclined about 12 degrees to the ecliptic. At aphelion, its farthest point, Sedna is about 200 astronomical units above the ecliptic plane. That's more than 6 times the distance from the Sun to Neptune, measured vertically. What could have created such an orbit? Sedna is too far from Neptune for that planet to have scattered it. Some astronomers think Sedna might have been perturbed by a passing star billions of years ago, or perhaps by a distant, undiscovered planet in the outer solar system. The mystery of Sedna's orbit is part of the larger mystery of what exists in the vertical dimensions beyond the Kuiper Belt. When we look at the distribution of known Kuiper Belt objects, we see a tapering effect. The number of objects decreases as we go to higher inclinations, but they don't disappear entirely. There's a long tail of the distribution, objects scattered into increasingly vertical orbits. These high inclination objects are harder to discover because they spend most of their time far from the ecliptic plane, in regions of the sky that sky surveys don't monitor as intensively. We're probably missing many such objects simply because we haven't looked for them in the right places. This realization is humbling. Even in the relatively nearby Kuiper Belt, our census is incomplete. We know there are objects out there, orbiting above and below the main concentration, that we simply haven't found yet. Each new discovery, like the 2004 discovery of the dwarf planet Haumea or the 2005 discovery of Eris, reminds us how much remains unknown. As we drift further outward in our exploration, leaving the Kuiper Belt behind and entering the realm of the inner Oort Cloud, the vertical dimension becomes increasingly significant. The disk-like structure of the inner solar system gives way to something more spherical, more three-dimensional. But that's a journey for our next chapter. For now, let's rest with the image of the Kuiper Belt, a gentle arc of icy worlds curving through the darkness, reaching both outward and upward, a transition zone between the familiar disk and the unknown sphere beyond. There's a region of our solar system that few people think about, a transition zone where the flat, disk-like structure of the inner solar system gradually transforms into the spherical structure of the Oort Cloud. This region doesn't have a single agreed-upon name, but it's sometimes called the inner Oort Cloud or the Hills Cloud, named after astronomer Jack Hills, who studied its dynamics in the 1980s. Imagine moving outward from the Sun, past the Kuiper Belt, past the scattered disk objects into the region beyond 1,000 astronomical units. Here, the familiar patterns of the inner solar system begin to break down. The gravitational influence of the planets becomes negligible. The Sun's gravity is still dominant, but it's weak, only barely holding on to the objects orbiting at these vast distances. At these distances, other forces become significant. The galactic tide, which we mentioned earlier, begins to affect orbits noticeably. The gravitational pull of nearby stars, though still distant, becomes relevant over the timescales of millions of years. These external influences can reshape orbits, twisting and tilting them, gradually randomizing their orientations. The transition from disk to sphere happens because of this randomization. Objects that originally formed in the disk of the early solar system, perhaps scattered outward by the giant planets, find their orbits slowly modified by external gravitational perturbations. An orbit that was initially close to the ecliptic plane might be tilted over time. Another orbit might be rotated in its orientation. Over millions and billions of years, these accumulated perturbations wash out the original disk structure. The result is that beyond a few thousand astronomical units, the distribution of objects becomes increasingly spherical. There's no longer a preferred plane of orbits. Objects circle the Sun from all angles, creating a vast, roughly spherical shell. This is the inner edge of the Oort Cloud, and it marks a fundamental shift in the architecture of the solar system. What's fascinating is that this transition happens gradually. There's no sharp boundary where the disk ends and the sphere begins. Instead, there's a zone, perhaps extending from 1,000 to 10,000 astronomical units, where both structures coexist. Closer in, disk-like properties dominate. Further out, spherical distribution takes over. In between, there's a mixture, a gradual blending. This transition zone is almost entirely unexplored. We've never sent a spacecraft through it. Our telescopes have barely detected a handful of objects that might reside there. Most of what we think we know comes from computer simulations and theoretical models. We input what we understand about the solar system's formation and evolution, about the effects of stellar encounters and galactic tides, and we calculate what the structure ought to be. But models aren't certainty. They're educated guesses, sophisticated hypotheses based on the physics we understand. The truth might be somewhat different. There might be unexpected structure in this transition zone, populations of objects we haven't predicted, dynamic processes we haven't considered. One possibility that's been suggested is that there might be a concentration of objects at certain distances where dynamical resonances occur with the galaxy's rotation. Just as planets can trap asteroids in orbital resonances, creating concentrations like the Trojan asteroids, the galaxy's structure might create subtle resonances that concentrate objects at specific distances from the Sun. Another possibility is that stellar encounters in the past might have stripped away some of this region, removing objects that were originally there. Our Sun formed in a cluster of stars, surrounded by siblings all born from the same giant molecular cloud. In the solar system's youth, the Sun was probably much closer to other stars than it is now. These early close encounters might have shaped the transition zone in ways we haven't fully understood. There's also the question of object composition. Are the objects in this transition zone still icy, like Kuiper Belt objects and Oort Cloud comets? Or might some be different? Perhaps rocky bodies scattered from the inner solar system, or even fragments of material captured from other stars in the Sun's birth cluster. The composition could vary with distance and with orbital inclination, creating a complex, layered structure. We simply don't know, and perhaps that's part of the beauty of contemplating this region. It's a genuine frontier, a place where human knowledge fades into uncertainty. When we imagine the space above and below the solar system at these distances, we're imagining something that no human has observed, something that exists in mathematical models and in physical reality, but not yet in confirmed observation. It's a space of potential, of possibility, of quiet mystery. To truly understand what's above and below our solar system, we need to contemplate the nature of gravity itself at these vast distances. Gravity is often described as an invisible force, but perhaps it's better thought of as the shape of space itself, curved by the presence of mass. The Sun, with its enormous mass, creates a deep well in the fabric of space, and objects near the Sun roll steeply down this well, orbiting quickly. But far from the Sun, the well is shallow, the curvature gentle, and objects move slowly in their vast orbits. At the distance of Earth, 1 astronomical unit from the Sun, the Sun's gravitational acceleration is about 6 millimeters per second squared. That might not sound like much, but it's enough to keep Earth whipping around the Sun at 30 kilometers per second, completing one orbit every year. Now move outward to Neptune, 30 astronomical units from the Sun. The gravitational acceleration has dropped by a factor of 900. It's now only about 0.006 millimeters per second squared. Neptune crawls around the Sun at just 5.4 kilometers per second, taking 165 years to complete a single orbit. Go further, to 1,000 astronomical units, deep in the transition zone we discussed in the previous chapter. The gravitational acceleration is now about 6 millionths of a millimeter per second squared. At this distance, if an object is in a circular orbit, it's moving at less than 200 meters per second, and it takes about 30,000 years to complete one orbit. At 10,000 astronomical units, approaching the inner regions of the Oort Cloud proper, the numbers become even more extreme. The gravitational acceleration is measured in billionths of a millimeter per second squared. Orbital velocities are tens of meters per second. Orbital periods stretch to hundreds of thousands of years. These numbers are almost incomprehensible. Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. An object orbiting at 10,000 astronomical units is moving so slowly that you could, in principle, keep pace with it in a car. Yet it's still bound to the Sun, still trapped in the gravitational well, still following an orbit that will eventually bring it around again, even if that eventually is 500,000 years in the future. What's particularly important for understanding the vertical dimensions of the solar system is that gravity acts equally in all directions. The Sun doesn't somehow pull more strongly on objects in the ecliptic plane than on objects above or below it. An object 10,000 astronomical units above the ecliptic plane feels exactly the same gravitational pull from the Sun as an object the same distance away but in the plane. This means that there's no gravitational reason why the outer solar system should be a disk. The disk structure of the inner solar system is a fossil, a remnant of the disk from which everything formed. But in the outer reaches, where external perturbations can change orbits over time, that original disk structure gets washed away. The spherical symmetry of gravity reasserts itself. But gravity's reach isn't infinite in a practical sense. At some distance, the Sun's gravitational influence becomes so weak that other forces can overcome it. The gravity of passing stars, the tidal force of the galaxy, even the gentle push of light pressure from distant massive stars, all these can perturb orbits or even strip objects away from the Sun entirely. The boundary where this happens defines the edge of the solar system, the limit of the Sun's gravitational domain. This boundary isn't sharp, and it varies depending on direction. In the direction toward the galactic centre, where the galactic tidal force is strongest, the boundary is closer. In other directions, it's farther away. Estimates for this boundary, often called the Hill sphere or the gravitational sphere of influence, range from about 50,000 astronomical units to over 100,000 astronomical units. That's 1 to 2 light years from the Sun. Objects beyond this distance aren't truly bound to the Sun. They might orbit for a while, but eventually external perturbations will either send them falling inward or pull them away entirely. This means that when we talk about what's above and below the solar system, we're ultimately talking about a spherical region roughly 1 to 2 light years in radius. Everything within this sphere is, or at least could be, part of the solar system. Everything beyond is the realm of interstellar space, the vast gulf between stars. Within this sphere, in the vertical dimensions above and below the ecliptic plane, there could be millions or even trillions of objects. Most would be small, icy bodies, remnants of the solar system's formation. A few might be larger, dwarf planets, or even planet-sized objects we haven't discovered. They orbit in the darkness, lit only by starlight, the sun reduced to just another bright star in their sky. And they've been doing this for billions of years, circling the sun so slowly that since the solar system's formation, they've completed only a few thousand orbits. They're the ultimate deep space objects, bound to our sun but barely, holding on at the very edge of gravitational possibility. When astronomers search for new objects in the solar system, they face a fundamental problem. The sky is vast, and the objects they're looking for are faint. This problem becomes especially acute when searching for objects in the vertical dimensions above and below the ecliptic plane. Most sky surveys, the systematic programs that sweep through the sky looking for moving objects, focus on regions near the ecliptic. There's a good reason for this. The vast majority of known solar system objects orbit close to the ecliptic plane, so that's where you're most likely to find something. If you have limited telescope time, it makes sense to focus your search where the density of targets is highest, but this creates a selection bias. By searching preferentially near the ecliptic, we're more likely to find objects near the ecliptic, which reinforces our impression that most objects orbit near the ecliptic, which justifies focusing our searches there. It's a circular logic that potentially blinds us to populations of objects in more vertical orbits. Imagine an object orbiting with a very high inclination, say 80 degrees to the ecliptic. Such an object would spend most of its time far from the ecliptic plane, passing through the plane only briefly as it crosses from the northern celestial hemisphere to the southern, or vice versa. If your sky survey only monitors regions within 20 or 30 degrees of the ecliptic, you might never see this object at all, or you might catch it only during its brief passage through the plane. And if the object is also on a very elongated orbit, spending most of its time at large distances from the sun where it's extremely faint, the chance of detection drops even further. You'd have to be looking at exactly the right patch of sky at exactly the right time, when the object is both near the ecliptic plane and close enough to the sun to be bright enough to detect. This isn't just hypothetical. There are known objects that were discovered almost by accident, objects whose orbits take them far from the ecliptic, and which were only found because they happened to be passing through the surveyed regions at the right time. Each such discovery raises the question, how many similar objects are out there that we simply haven't found yet? In recent years, some sky surveys have begun to expand their coverage to higher ecliptic latitudes, searching further above and below the plane. The Panoramic Survey Telescope and Rapid Response System, known as PAN-STARRS, operating from Hawaii, surveys a large fraction of the sky accessible from its latitude. The Catalina Sky Survey, operating from Arizona, also covers a substantial area. These surveys have discovered numerous objects with moderate to high inclinations, including some scattered disk objects and detached objects with inclinations of 30 to 40 degrees or more. Each discovery helps fill in our understanding of the true three-dimensional structure of the outer solar system, but even these surveys have limitations. They're optimized for finding near-Earth asteroids and comets, objects that might pose a hazard to our planet. Such objects are bright enough to detect when they're close to Earth, but a similar-sized object in the outer solar system, even if it's in a highly inclined orbit that brings it close to our latitude, might be far too faint to see. What we really need to map the vertical dimensions of the solar system is a dedicated survey designed specifically for this purpose. Such a survey would systematically search the sky at all latitudes, looking for faint, slow-moving objects that betray their distance by how slowly they drift against the background stars. It would require a large telescope, sensitive cameras, and years of patient observation. Some projects are moving in this direction. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time, which will repeatedly image the entire southern sky every few nights. This survey will undoubtedly discover many new outer solar system objects, including those in vertical orbits. but we should be realistic about what even these ambitious surveys can achieve. The outer solar system is vast, and objects there are incredibly faint. Even a dedicated survey will only scratch the surface, finding the largest and closest members of these distant populations. The complete census of what's above and below our solar system may be something that remains beyond our reach for generations to come. There's something both frustrating and wonderful about this limitation. It means that even our own solar system, our cosmic backyard, contains mysteries we can't easily solve. It means there are still blank spaces on the map, regions labelled "Here be dragons," not because of real dangers, but because of genuine ignorance. For all our technology and our knowledge, we remain cosmically provincial, aware of the nearby and ignorant of the distant. Among the objects orbiting in the vertical dimensions of our solar system, some are large enough to warrant the classification of dwarf planet. These are worlds in their own right, rounded by their own gravity, but exiled from the familiar plane of the major planets, following lonely paths through the outer darkness. Pluto is perhaps the most famous example, though its inclination of 17 degrees, while notable, isn't extreme compared to some other objects. Pluto's elliptical orbit takes it from about 30 to 50 astronomical units from the Sun, and at its most inclined point, it's about 14 astronomical units above or below the ecliptic plane. That's roughly the distance from the Sun to Uranus, measured vertically. When Pluto is at these extreme latitudes, it's viewing the solar system from an angle we never experience on Earth. From Pluto's perspective at high latitude, the ecliptic plane would appear tilted, and the major planets would all be clustered in one relatively narrow band across the sky. It would be obvious, even to a casual observer on Pluto, that the solar system has a preferred plane and that Pluto isn't in it. Then there's Eris, discovered in 2005, the object whose discovery prompted the reclassification of Pluto from planet to dwarf planet. Eris is slightly more massive than Pluto, but it orbits much farther from the Sun, with an extremely elongated orbit that takes it from about 38 astronomical units to 97 astronomical units. Its inclination is a dramatic 44 degrees. At aphelion, its farthest point from the Sun, Eris is about 67 astronomical units above the ecliptic plane. That's more than twice the distance from the Sun to Neptune measured vertically. From Eris at aphelion, the solar system must look remarkably different. The Sun is just a bright star, no longer a disk, but a point of light. The ecliptic plane containing all the major planets is far below, a distant realm that Eris only visits briefly once every 557 years. What might Eris look like? We don't know for certain, but spectroscopic observations suggest it's covered in a layer of methane ice, giving it a bright, white appearance. In the cold at 97 astronomical units from the Sun, methane doesn't sublimate. It simply lies there, frozen on the surface, reflecting what little sunlight reaches it. Eris has a moon, Dysnomia, orbiting around it. Together the pair drift through the vertical reaches of the outer solar system, a tiny binary world far from the familiar territories. One wonders what it would be like to stand on Eris and look up at Dysnomia in the sky, or, vice versa, to be an observer in this remote realm where Earth and all the inner planets are lost in the Sun's glare, invisible, irrelevant. There are other dwarf planet candidates with significant inclinations. Makemake, another large Kuiper Belt object, has an inclination of about 29 degrees. Haumea, an unusually elongated dwarf planet that spins rapidly, has an inclination of 28 degrees. These worlds, along with numerous smaller bodies, form a population of high-inclination large objects that we're only beginning to census. What's particularly intriguing is that some of these dwarf planets might have formed in the vertical dimensions where they now orbit, or they might have been scattered there from elsewhere. The answer to this question tells us about the history of the solar system, about the violence of the planet formation process and the early dynamical evolution. If these objects formed in place, high above or below the ecliptic, It would suggest that the protoplanetary disk was thicker than we usually imagine, or that there were processes during formation that could create vertical structure. Alternatively, if they formed closer to the ecliptic and were scattered to their current orbits, it tells us about the power of gravitational interactions in the early solar system. Current thinking favours the scattering hypothesis for most high-inclination dwarf planets. Models of the solar system's early evolution, particularly the Nice model, which describes a period of dynamical instability among the giant planets, suggest that massive numbers of objects were scattered into inclined orbits during this chaotic period. Some of these were ejected from the solar system entirely, some crashed into the sun or planets, and some ended up in the scattered disk and Oort Cloud. But certainty is elusive. Each new discovery in the outer solar system brings surprises. In 2014, astronomers discovered an object designated 2012 VP113, nicknamed Biden, after Vice President Joe Biden. This object has an orbit that never comes closer than 80 astronomical units to the Sun, making it more detached from planetary influence than even Sedna. Its inclination is about 24 degrees, and at aphelion, it's hundreds of astronomical units above the ecliptic. Objects like this hint at populations we haven't yet characterized. How many dwarf planets are out there in vertical orbits? How many planet-sized bodies might be lurking in the darkness, too far and too faint for current surveys to detect? These questions remain open, waiting for future observations to provide answers, or at least better constraints. Let's contemplate something subtle but profound. The solar system isn't static. Objects don't simply orbit forever in fixed paths. Their orbits slowly evolve, gradually changing over millions of years due to various dynamical processes. This means that material can migrate vertically through the solar system, objects slowly moving from low inclination orbits to high inclination orbits, or vice versa. One of the key mechanisms for this vertical migration is the Kozai mechanism. Named after Yoshihide Kozai, who described it in 1962. The Kozai mechanism occurs when an object's orbit is perturbed by a distant massive body. Under certain conditions, this perturbation can cause the object's inclination and eccentricity to oscillate in a coupled way. As the eccentricity increases, the inclination decreases, and vice versa. Imagine an object in the scattered disk, currently in a moderately eccentric, moderately inclined orbit. If a distant star passes through the outer solar system, or if the galactic tide acts on the object over many orbits, the Kozai mechanism might be triggered. The object's orbit could begin to oscillate, its eccentricity and inclination trading off. Over thousands or millions of years, an orbit that started at a modest inclination could reach very high inclinations, sending the object far above or below the ecliptic plane. This mechanism is thought to be important in the outer solar system, particularly in the Oort Cloud. It might help explain how objects initially scattered outward in relatively low inclination orbits can end up in the highly inclined or even retrograde orbits characteristic of many Oort Cloud comets. Another process is simple perturbations from passing stars. As we've mentioned, the Sun isn't alone in space. Other stars pass by, some relatively close in cosmic terms. A star passing a few tens of thousands of astronomical units from the Sun can gravitationally perturb the orbits of Oort Cloud objects, changing their inclinations, eccentricities, and orientations. These stellar encounters happen occasionally on astronomical timescales. Over the 4.5 billion years since the solar system formed, there have been perhaps dozens of encounters close enough to significantly affect the Oort Cloud structure. Each encounter stirred the cloud, randomizing orbits, increasing the overall sphericity of the distribution. There's also the continuous subtle influence of the galactic tide. The Milky Way's gravitational field isn't uniform. As the Sun orbits the galactic centre, completing one orbit every 230 million years or so, it passes through regions of varying stellar density. The tidal force from the galaxy torques the orbits of distant solar system objects, gradually changing their orientations and inclinations. Over billions of years, this galactic tide has helped sphericalize the Oort Cloud, taking what was probably originally a more disk-like distribution and transforming it into the roughly spherical shell we think exists today. It's a slow process, but given enough time, it's extraordinarily effective. What's fascinating is that this vertical migration isn't just ancient history. It's ongoing. Objects are migrating vertically through the solar system right now, their orbits slowly changing under the influence of distant perturbations. A Kuiper Belt object currently in a low inclination orbit might, over the next 100 million years, have its inclination excited by some gravitational interaction, sending it into the vertical dimensions. Similarly, an object currently in a high inclination orbit might have its inclination damped by some process, bringing it back closer to the ecliptic plane. The traffic goes both ways, a slow exchange between the disk and the sphere, between the horizontal and the vertical dimensions of the solar system. This ongoing evolution means that the vertical structure of the solar system is dynamic. It's not a frozen remnant of ancient events, but an active, changing system. What we see today is just a snapshot, a moment in a 4.5 billion year evolution that will continue for billions of years into the future. There's also the question of how material enters the vertical dimensions in the first place. We've talked about scattering by the giant planets, about stellar encounters, about the Kozai mechanism and galactic tides. But there's another possibility. Some material in the vertical dimensions might not have originated in our solar system at all. Interstellar objects, visitors from other star systems, pass through our solar system occasionally. In 2017, we detected the first confirmed interstellar object named Oumuamua. In 2019, we detected a second, the interstellar comet Borisov. These objects were just passing through, following hyperbolic trajectories that brought them in from interstellar space, swung them past the Sun, and sent them back out again. But it's possible that some interstellar objects don't escape. If an interstellar object enters the solar system at just the right speed and angle, and if it happens to make a close pass by one of the giant planets, it could be captured, its orbit change from hyperbolic to elliptical. Once captured, it would become a permanent member of the solar system. Captured interstellar objects might preferentially end up in high inclination orbits, because that's where capture is most likely. An object coming in from interstellar space is likely to have a velocity vector oriented randomly relative to the ecliptic plane. If captured, its orbit would retain some of that random orientation, resulting in a high inclination orbit. How many objects in the vertical dimensions of the solar system might be captured interstellar visitors? We don't know. But it's a tantalizing possibility. Every high inclination object we discover could potentially be a visitor from another stellar system, carrying with it information about planet formation elsewhere in the galaxy. As we contemplate this vertical migration of matter, this slow exchange between different regions of the solar system, and even between the solar system and interstellar space, we're seeing the solar system as something fundamentally dynamic. It's not a clock, wound up at formation and ticking predictably ever since. It's more like a living system, constantly exchanging material and energy with its environment, evolving, changing, growing, and yes, aging. The vertical dimensions above and below the ecliptic are part of this dynamic system. Reservoirs and pathways for migrating matter, connecting the familiar disk to the vast sphere beyond. We've reached a threshold in our journey, a boundary where the last remnants of disk structure fade away entirely and we enter truly spherical territory. This is the Oort Cloud proper, the vast shell of icy bodies that surrounds the solar system at distances so great that the sun's influence becomes tenuous, a whisper rather than a shout. The Oort Cloud is named after Dutch astronomer Jan Oort, who proposed its existence in 1950. Oort was studying the orbits of long-period comets, those comets that take hundreds, thousands, or even millions of years to complete a single orbit around the Sun. He noticed something peculiar. These comets approached the Sun from all directions equally. There was no preference for the ecliptic plane, no concentration in any particular region of the sky. This uniform distribution suggested that these comets were coming from a spherical reservoir, not a disk. Oort calculated that this reservoir must be at tremendous distances from the Sun, perhaps tens of thousands of astronomical units or more. The comets we occasionally see are ones whose orbits have been perturbed, sending them falling inward from this distant shell. We now think the Oort cloud has two components, an inner Oort cloud or Hills cloud extending from perhaps a few thousand to 20,000 astronomical units, and an outer Oort cloud extending from 20,000 to possibly 100,000 astronomical units or more. The inner cloud retains some disk-like properties, though much diluted compared to the Kuiper Belt. The outer cloud is genuinely spherical. Let's try to comprehend these distances. 20,000 astronomical units is about 1/3 of a light year. Light from the Sun takes about 4 months to reach this distance. If you could somehow stand on an object in the inner Oort cloud and look back at the Sun, you'd see it as a bright star, but no longer the dominant object in the sky. The other stars wouldn't appear much dimmer than the Sun. You'd be in a twilight realm, neither fully in the solar system nor truly in interstellar space. At 50,000 astronomical units, approaching the outer edge of the Oort cloud, the Sun would be just one star among many, still the brightest from your location, but not overwhelmingly so. Light from the Sun takes nearly a year to reach this distance. This is where the Sun's gravitational dominance truly ends, where other stars' gravity becomes comparable in strength. How many objects are in the Oort cloud? Estimates vary wildly, but some models suggest there could be trillions of icy bodies larger than 1 kilometre across. The total mass might be anywhere from a few Earth masses to tens of Earth masses, though uncertainties are enormous. We've never directly detected an Oort cloud object except when one has fallen inward and become a comet, so all our estimates are based on extrapolation and modelling. What are these objects made of? Almost certainly ices, water ice, methane ice, ammonia ice, carbon dioxide ice, mixed with rocky dust and organic compounds. They're pristine samples of the material from which the solar system formed, unchanged by the Sun's heat. Preserved in the deep freeze for 4.5 billion years. Each object is on its own orbit, a vast ellipse that carries it around the Sun over periods ranging from hundreds of thousands to tens of millions of years. The orbital velocities are minute, measured in tens or hundreds of meters per second. 2 Oort cloud objects could pass within a few kilometers of each other, each creeping along its orbit, and they might barely notice one another's presence. So weak is their mutual gravity at these scales. Imagine the loneliness of an Oort cloud object. It formed in the warmth and chaos of the inner solar system, back when the planets were assembling, when collisions were frequent and the sky was filled with planetesimals. Then it was scattered outward, flung into the outer darkness by a close encounter with Jupiter or Saturn. It climbed for millions of years, slowing as it fought against the Sun's gravity, until finally it reached aphelion, its farthest point, perhaps 50,000 astronomical units from the light and heat that created it. There it hangs, nearly motionless, for perhaps 1,000,000 years before it begins the long fall back inward. But it will never again approach the realm of the planets. Its perihelion, its closest approach to the Sun, is still thousands of astronomical units away. It will spend eternity in the outer darkness, only occasionally disturbed by the passage of a distant star. And yet it remains bound to the Sun. Despite the enormous distance, despite the faintness of the Sun's light and the weakness of its gravitational pull, the object is still part of the solar system. It's still orbiting, still following the laws that govern all orbits, still connected by invisible threads of gravity to the star that birthed it. The Oort cloud is the final province of the Sun's empire, the outermost territory that still acknowledges its rule. Beyond the Oort cloud lies interstellar space, the realm between stars where the Sun's influence fades to nothing and other stars' gravity takes over. But within the cloud, even at these absurd distances, the Sun is still sovereign, still holding on to its distant subjects through the weakest of gravitational tethers. One of the most striking features of the Oort Cloud, and one that makes it fundamentally different from the inner solar system, is its symmetry. In the inner solar system, as we've discussed, there's a strong preference for the ecliptic plane. Most objects orbit near this plane, creating a disk-like structure. But in the Oort Cloud, there's no such preference. Objects orbit equally above and below the ecliptic to the north and south in all directions. This spherical symmetry is profound. It means that if you could somehow mark a spot 10,000 astronomical units directly above the Sun, perpendicular to the ecliptic plane, and another spot 10,000 astronomical units below the Sun on the opposite side, and a third spot 10,000 astronomical units to the side in the ecliptic plane, all three locations would be essentially identical in terms of Oort Cloud properties. Each would have roughly the same density of objects, the same distribution of sizes and compositions. Why does this symmetry exist? As we've explored, it's the result of billions of years of gravitational perturbations that have randomized the orbits of objects in the Oort Cloud. The original disk-like distribution from the solar system's formation has been erased, replaced by a spherical shell. This erasure is remarkably complete. Computer simulations of the Oort Cloud's evolution suggest that any initial disk-like structure would be completely randomized within 1 billion years or so. Given that the solar system is 4.5 billion years old, the Oort Cloud has had more than enough time to achieve complete spherical symmetry. What this means is that the vertical dimensions of the Oort Cloud are just as populated as the horizontal dimensions. If we imagine a cylinder extending upward from the Sun, perpendicular to the ecliptic plane, and another cylinder extending sideways in the ecliptic plane, both cylinders with the same radius and length, they would contain the same number of Oort Cloud objects. This is very different from the inner solar system. If we drew similar cylinders through the Kuiper Belt, for example, the horizontal cylinder would contain far more objects than the vertical one. The Kuiper Belt is still fundamentally a disk, despite its vertical thickness. The Oort Cloud's spherical symmetry has practical implications for how we observe comets. Because Oort Cloud comets can approach the Sun from any direction, they're discovered at all different latitudes in the sky. Northern Hemisphere observatories find comets coming from the north. Southern Hemisphere observatories find comets from the south, and both find comets that pass close to the ecliptic plane. The distribution is uniform. This wasn't always understood. In the early days of comet astronomy, there was some debate about whether comets came preferentially from certain directions. But as more comets were discovered and their orbits calculated, the pattern became clear. Truly long-period comets show no directional preference. They come from all directions equally, exactly as you'd expect from a spherical reservoir. There's something almost philosophical about this symmetry. In the inner solar system, we have a sense of orientation. The ecliptic plane is special. It's where the planets are, where most of the action happens. Up and down have meaning relative to this plane. We can imagine being, quote, for the solar system, looking down on it, seeing the planets laid out in their orbital paths like a clockwork display. But in the Oort Cloud, this orientation loses meaning. There's no special direction, no plane of preference. Up and down, north and south, these are arbitrary labels we impose for our own convenience. From the Oort Cloud's perspective, all directions are equivalent. The ecliptic plane is just one plane among infinite possible planes, with no special status. This might seem like a trivial observation, but it represents a genuine shift in perspective. When we think about the solar system, we usually think in terms of the disk, the Sun at the centre, the planets in their orbits, all laid out in a flat configuration that we can visualize easily. But the Oort Cloud forces us to think three-dimensionally, to imagine a truly spherical system where our usual mental models don't apply. Perhaps there's a metaphor here about expanding our perspectives, about moving beyond familiar patterns into more complex multi-dimensional thinking. The solar system, in its full extent, isn't the simple disk we often imagine. It's a sphere, vast and symmetrical, extending equally in all directions from the Sun, and in this sphere, the regions above and below the ecliptic plane are just as real, just as populated, just as much a part of the solar system as the familiar plane itself. When we look up into the night sky, away from the ecliptic where the planets wander, we're not looking at empty space above the solar system. We're looking through the Oort Cloud, through regions filled with distant, invisible objects that are as much a part of our solar system as the planets themselves. The vertical dimensions aren't some exotic frontier or strange exception. They're half of reality, the half we tend to forget because it's not where the bright visible objects are. But in terms of volume, in terms of the space occupied by solar system objects, the vertical dimensions dominate. The disk is the anomaly, the special case. The sphere is the norm. At the very outermost edge of the Oort Cloud, perhaps 75,000 to 100,000 astronomical units from the Sun, we find the most loosely bound objects in the entire solar system. These are bodies that are barely held by the Sun's gravity, objects that could be pulled away by a passing star or by the tidal force of the galaxy. They represent the ultimate limit of the Sun's gravitational reach. Imagine an object orbiting at 100,000 astronomical units from the Sun. At this distance, the Sun's gravitational acceleration is measured in trillionths of a metre per second squared. If this object is in a circular orbit, it's moving at about 40 metres per second, roughly the speed of a car on a highway. Its orbital period is about 30 million years. 30 million years is an almost incomprehensible span of time. When this object last completed an orbit, the Oligocene epoch was ending on Earth. The first grasslands were spreading across continents. Early apes were evolving in Africa. 30 million years from now, if it completes its next orbit, who knows what Earth will be like, or whether humans will still exist to observe it. But the orbit itself is precarious. At these distances, the Sun's gravity is only barely stronger than the perturbations from other forces. A star passing within a few light years could pull this object away from the Sun entirely, stealing it into interstellar space. The galactic tide could gradually increase the object's orbital energy until it too escapes. Computer simulations suggest that the outer Oort cloud is slowly evaporating. Objects at these extreme distances are being stripped away by stellar encounters and galactic tides at a rate such that the outer cloud will largely disappear over billions of years. The Oort cloud we observe today is probably less massive than it was when the solar system was young, eroded by 4.5 billion years of perturbations. This raises a poignant question. Are there objects currently in interstellar space that once belonged to our solar system? Objects that were part of the Oort cloud but have been pulled away, now drifting between the stars, no longer bound to the Sun? Almost certainly yes. Models suggest that over the solar system's lifetime, a significant fraction of the original Oort cloud has been lost to interstellar space. These lost objects are now travelling through the galaxy, perhaps encountering other star systems, perhaps being captured by other stars. They're exiles, no longer part of the solar system but carrying with them the chemical signature of their origin. Conversely, our Oort cloud might contain objects that originated around other stars. If our Sun can lose Oort cloud objects, then other stars can too. When two stars pass close to each other, they might exchange Oort cloud objects, with each star capturing some of the other's outer comets. Over billions of years and many stellar encounters, the Oort cloud might be a mixture, mostly objects formed in our solar system, but with a contribution of foreign objects captured from elsewhere. We have no way to tell these apart. An object in our Oort cloud that originated around another star would look the same as a native object. Same icy composition. Same orbit. Nothing to mark it as alien. Only if we could analyse its isotopic composition in extreme detail might we find subtle differences that hint at an origin in a different part of the galaxy with a slightly different chemical history. There's something beautifully democratic about this exchange. Stars sharing their Oort clouds, trading objects back and forth over galactic timescales. The solar system isn't isolated. It's part of a larger galactic ecosystem, exchanging matter with neighbouring stars, connected to them through these tenuous interactions. But let's return to the vertical dimension specifically. At 100,000 astronomical units, about 1.5 light-years from the Sun, an object directly above the ecliptic plane is just as distant, just as loosely bound as an object in the ecliptic plane itself. The vertical and horizontal dimensions are equivalent at these scales. This means that the solar system's vertical extent is just as large as its horizontal extent. When we ask how big the solar system is, the answer depends on which dimension we're measuring. In the plane of the planets, from the Sun to Neptune, it's about 30 astronomical units. But from the ecliptic plane upward to the top of the Oort cloud, it's 100,000 astronomical units or more. The vertical dimension is thousands of times larger than the horizontal planetary dimension. If we drew the solar system to scale, including the Oort cloud, with the Sun at the centre, it would be almost perfectly spherical. The flattened disk of planets would be an imperceptibly thin layer at the very centre of this sphere. Everything else, more than 99.9% of the solar system's volume, would be the roughly spherical Oort cloud. This is the reality that we overlook when we think about the solar system. The disk is real, but it's tiny. The sphere is vast and it extends equally above, below and to the sides. The vertical dimensions aren't some marginal region. They're the bulk of the solar system, the majority of its volume and its spatial extent. Standing on Earth, looking up into the night sky, we're at the centre of this sphere, looking outward through its depths. Every direction we look, we're looking through the Oort cloud. It's all around us, above us, below us, to all sides, a vast shell of objects so distant and faint that we can't see them, but present nonetheless, defining the true scale of our solar system. The orbits of objects in the Oort cloud, particularly those in the vertical dimensions far above and below the ecliptic plane, are shaped by forces that are negligible in the inner solar system. To understand these distant orbits, we need to think beyond simple two-body dynamics, the Sun and an object orbiting around it, and consider the subtle influences of the galaxy itself. The Milky Way galaxy is a vast rotating disk of stars, gas and dark matter. Our Sun is located about 26,000 light-years from the galactic centre, orbiting around it at about 230 kilometers per second. This orbit takes roughly 230 million years to complete, a period sometimes called a galactic year. As the Sun orbits, it moves through the galaxy's gravitational field. This field isn't uniform. Near the galactic plane, where most of the galaxy's mass is concentrated, the gravitational pull is stronger. Above and below the plane, it's weaker. This creates a tidal force, a gravitational gradient that can affect the orbits of distant solar system objects. For objects in the inner solar system, this galactic tidal force is completely negligible. Earth, for example, feels the Sun's gravity billions of times more strongly than the galaxy's tide. But for an Oort cloud object at 50,000 astronomical units, the situation is different. The Sun's gravity is weak there, and the galactic tide becomes relatively significant. The galactic tide can torque the orbits of Oort cloud objects, slowly changing their orientations and inclinations over time. An object initially orbiting in the ecliptic plane might gradually have its orbit tilted, lifted out of the plane into the vertical dimensions. Conversely, an object in a highly inclined orbit might be brought back closer to the plane. The timescales for these changes are long, millions to tens of millions of years. But given the billions of years since the solar system formed, the galactic tide has had enormous cumulative effect. It's one of the primary mechanisms that sphericalize the Oort cloud, randomizing the orientations of orbits so that no plane is preferred. There's also the radial tidal force, which tends to stretch out orbits, increasing their eccentricity. This can turn a nearly circular orbit into an elongated ellipse, and in extreme cases it can unbind objects entirely, pulling them away from the Sun into interstellar space. Another important force is the gravitational influence of passing stars. The Sun isn't stationary, it's moving through the galaxy, occasionally passing close to other stars. Every few million years, on average, a star passes within about 1 light-year of the Sun. Every few 100 million years, a star might pass within about 1/10 of a light-year, close enough to significantly disturb the outer Oort Cloud. When a star passes close, its gravity can perturb the orbits of Oort Cloud objects dramatically. Objects in the outer cloud, especially those in the vertical dimensions at large distances from the ecliptic plane, can have their orbits change suddenly. Some might be pulled away from the Sun entirely, captured by the passing star or set loose in interstellar space. Others might have their perihelion distances decreased, sending them falling inward toward the Sun to become visible comets. These stellar encounters are believed to be the primary mechanism that sends Oort Cloud comets into the inner solar system. An object peacefully orbiting in the outer cloud for billions of years gets perturbed by a passing star. Its perihelion drops from, say, 10,000 astronomical units to just a few astronomical units. It begins the long fall inward, accelerating as the Sun's gravity strengthens, and eventually it sweeps past the Sun close enough to heat up and develop a visible coma and tail. From our perspective on Earth, a new comet appears in the sky. But from the comet's perspective, it's been woken from a 4 billion year slumber, ripped from the quiet, cold darkness of the outer cloud, and sent careening into the bright chaos of the inner solar system. It's a traumatic journey, one that will likely result in the comet's destruction, either by sublimation as it loses its volatile ices near the Sun, or by fragmentation under thermal stress. The direction from which stellar encounters come is random. Stars in the Sun's neighbourhood are moving in all directions relative to the Sun, orbiting the galaxy at slightly different speeds and on slightly different paths. This means that stellar encounters perturb Oort Cloud objects equally in all directions. There's no preferred direction for perturbations, which contributes to the spherical symmetry of the cloud. In the vertical dimension specifically, stellar encounters can create orbits that are nearly perpendicular to the ecliptic plane, or even retrograde, orbiting in the opposite direction to the planets. These exotic orbits are impossible to create through interactions with the planets alone, which is why they're a signature of Oort Cloud origin. There's also a subtle effect from radiation pressure. Light from the Sun, even at Oort Cloud distances, carries momentum. When photons strike an object, they impart a tiny push. For small objects, dust grains, or very small icy bodies, this radiation pressure can be significant enough to affect their orbits over long timescales. Radiation pressure acts radially outward from the Sun, pushing objects away. For very small particles, this push can overcome the Sun's gravity entirely, and the particles are expelled from the solar system. This is why the Oort Cloud likely doesn't contain much in the way of dust. Any dust formed by collisions between larger objects would be blown away by radiation pressure within a relatively short time. For larger objects, radiation pressure is negligible compared to gravity, but it's not zero. Over millions of years, it might contribute to subtle orbital changes, particularly for objects in very weak orbits at the outer edge of the cloud. All these forces, galactic tides, stellar encounters, radiation pressure, interact in complex ways to shape the orbits we observe. The vertical dimensions of the Oort Cloud are a product of this complexity, a region where simple Keplerian orbits around the Sun give way to more complicated dynamics involving external influences. It's a reminder that the solar system, especially in its outer reaches, isn't an isolated system. It's embedded in the galaxy, subject to galactic forces, interacting with other stars, part of a larger cosmic environment that shapes its structure and evolution. What are conditions like in the vertical dimensions of the Oort Cloud, In the cold darkness, tens of thousands of astronomical units above and below the ecliptic plane, it's a realm so remote and so hostile to life as we know it that it's difficult to imagine, yet worth contemplating for what it tells us about the extremes of the solar system. Let's start with temperature. At 1 astronomical unit from the Sun, at Earth's distance, the effective temperature of a black body in sunlight is about 279 Kelvin, or 6 degrees Celsius. This is the temperature an object would reach if it absorbed all the sunlight hitting it, and radiated that energy away as thermal radiation, with no atmosphere or internal heat sources. At Neptune's distance, about 30 astronomical units, this temperature drops to about 46 Kelvin, or negative 227 degrees Celsius. It's cold, but still well above absolute zero. Now consider 50,000 astronomical units, deep in the Oort Cloud. The intensity of sunlight drops with the square of the distance, so at 50,000 astronomical units, sunlight is about 2.5 million times weaker than at Earth. The effective temperature of a black body there would be about 3 Kelvin, just 3 degrees above absolute zero. But it's actually slightly warmer than that because of the cosmic microwave background radiation, the faint glow left over from the Big Bang. The CMB has a temperature of about 2.7 Kelvin and is present everywhere in the universe. For an object in the outer Oort cloud, the CMB provides more heat than sunlight does. The Sun has become irrelevant as a heat source. The object's temperature is set by the background radiation of the entire universe. So an object in the vertical dimensions of the outer Oort cloud, 50,000 astronomical units above or below the ecliptic plane, would have a surface temperature of about 3 Kelvin, dominated by the CMB. At this temperature, essentially all substances are frozen solid. Water ice, methane ice, nitrogen ice, even hydrogen and helium in extreme cases, all are frozen. The object is in darkness. Not pitch black, but illuminated only by starlight and the faint glow of the CMB. The Sun is visible as a bright star, brighter than any other star in the sky, but no longer a disk, just a point of light. You couldn't use sunlight to read by or to warm yourself. The Sun has become just another star, special only in being brighter than the rest. If you could stand on such an object, setting aside the impossibility of surviving there, what would you see? Looking outward, you'd see the stars, vast numbers of them undimmed by any atmosphere, wheeling slowly overhead as the object rotates, if it rotates. Some Oort cloud objects might not rotate at all, or might rotate so slowly that a quote 5 lasts years or centuries. Looking toward the Sun, you'd see the familiar constellations, but with one star slightly brighter than it should be. That's our Sun, the star around which you're orbiting, though at such distance and with such a long period that the concept of orbiting becomes almost abstract. The Sun doesn't appear to move in the sky over your lifetime or over 100 lifetimes. Its motion is imperceptible. Looking to the sides, perpendicular to the line to the Sun. You might see other Oort cloud objects if any are close enough, and if you have a very good telescope. But space is vast even in the Oort cloud. The average distance between objects might be tens or hundreds of billions of kilometres. Your nearest neighbour could be light weeks or light months away. The silence would be absolute. There's no air to carry sound, of course, but more than that, there's no activity. No wind, no weather, no geological processes. The object is geologically dead. Frozen solid with no internal heat source to drive any kind of activity. If it was ever active, that was billions of years ago when it first formed. Since then, nothing has changed. The surface is exactly as it was left, preserved by the cold. Time passes differently here. Chemical reactions are essentially frozen out at 3 Kelvin. Radioactive decay continues, but even that is slow compared to geological timescales. An object could sit here for billions of years and undergo essentially no change. It's preservation in the most perfect sense. A museum of the early solar system, each object a pristine sample of the material from which planets formed. If a stellar encounter perturbs such an object, sending it falling toward the Sun, the journey inward is itself a transformative event. As the object approaches the inner solar system, it begins to warm. At some distance, perhaps 10 or 20 astronomical units from the Sun, the most volatile ices on its surface begin to sublimate. Nitrogen, carbon monoxide, methane. These ices turn directly from solid to gas without melting, creating a thin atmosphere that immediately escapes into space. Closer still, water ice begins to sublimate, and the object develops the characteristic coma and tail of a comet. Jets of gas erupt from the surface, driven by the pressure of sublimating ice. The object might begin to spin faster as jets act like tiny rocket engines, torquing it. It might fracture from thermal stress, unused to the sun's heat after billions of years in the cold. This transformation, from frozen museum piece to active comet, happens over the course of years or decades as the object falls inward. It's a one-way journey. Once heated, once its volatile ices have sublimated away, the object can never return to its original state. Even if its orbit takes it back to the Oort Cloud after it's passed by the Sun, it will return changed, depleted, its surface crust altered by exposure to heat. But most objects in the vertical dimensions of the Oort Cloud will never make this journey. They'll remain in the cold forever, or at least for billions of years until the Sun itself dies. They're archives, waiting silently in the dark, preserving information about the solar system's origin, about the molecular cloud from which the Sun formed, about the conditions in the early solar nebula. If we could visit one, if we could send a spacecraft to the Oort Cloud and sample one of these objects, we would learn so much. We'd be holding a piece of the original solar system, unchanged since formation. We could analyse its composition in detail, measure its isotopic ratios, study its structure, and from that data refine our understanding of how the Sun and planets formed. But such a mission is beyond our current capabilities. The distances are too vast, the travel times too long. Voyager 1, our most distant spacecraft, is currently about 160 astronomical units from the Sun, moving at about 3.5 astronomical units per year. At this rate, it would take about 15,000 years to reach the inner edge of the Oort Cloud, and it's not even heading in the right direction. So for now, the objects in the vertical dimensions of the Oort Cloud remain unexplored, known only through inference and theory. They're out there, we're quite confident of that, but we've never seen one in situ. We've only seen the ones that fell inward and became comets, the ones that left the quiet dark and entered the light. The vast majority remain hidden, perhaps forever beyond our reach, silent witnesses to solar system history. One of the most intriguing questions about the solar system's vertical dimensions is whether there might be undiscovered planets orbiting far above or below the ecliptic plane. It's a question that sounds like science fiction but is actually grounded in serious scientific possibility, and it becomes particularly relevant when we consider recent hypotheses about Planet 9. Planet 9 is a hypothesized planet in the outer solar system, proposed by astronomers Konstantin Batygin and Mike Brown in 2016. Their proposal was based on observations of unusual clustering in the orbits of several distant objects beyond Neptune. These objects' orbits seem to be aligned in a way that would be unlikely by chance, and computer simulation suggested that this alignment could be explained by the gravitational influence of a large undiscovered planet. The proposed Planet 9 would be several times the mass of Earth, orbiting at several hundred astronomical units from the Sun. Its orbital period would be 10 to 20,000 years. And here's what's relevant to our exploration. Some versions of the Planet 9 hypothesis suggest it could have a fairly high orbital inclination, perhaps 15 to 25 degrees, or even more. If Planet 9 exists and has a high inclination, it would spend much of its time well above or below the ecliptic plane. At an inclination of, say, 20 degrees and a distance of 600 astronomical units, the planet could be over 200 astronomical units above or below the ecliptic. That's 7 times Neptune's distance from the Sun, measured vertically. This raises a fascinating possibility. Could there be a planet-sized object in our solar system that we've never seen because it's in the vertical dimensions, far from the ecliptic where most searchers concentrate? The answer is maybe, though with important caveats. First, while sky surveys do focus on the ecliptic region, they're not blind to other areas. Major surveys like Pan-STARRS and the Catalina Sky Survey cover substantial portions of the sky at all latitudes. If there's a planet several times Earth's mass within a few hundred astronomical units, it should be bright enough to have been detected by these surveys, regardless of its inclination. However, if the planet is currently near aphelion and also at high ecliptic latitude, the combination of distance and position might have made it faint enough to escape detection so far. Or if it's on an orbit with very high inclination, it might be in a region of the sky that hasn't been surveyed as intensively. Second, planets don't necessarily form in high inclination orbits. The process of planet formation in the protoplanetary disk naturally produces planets orbiting close to the disk's plane. To get a planet into a high inclination orbit, you need some mechanism to lift it out of the plane. One possibility is gravitational scattering. If there was another massive planet in the early solar system, one that has since been ejected, it could have scattered what we now call Planet 9 into an inclined orbit during the scattering event. Alternatively, an encounter with a passing star early in the 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. An encounter with a passing star early in the solar system's history could have tilted the orbit. Another possibility, more exotic, is that Planet 9 didn't form in our solar system at all. It might be a captured rogue planet, a planet that formed around another star, was ejected from that system, and later encountered our solar system and was gravitationally captured. Captured planets would be expected to have randomly oriented orbits, including high inclination orbits. The idea of a rogue planet sounds fantastical. But astronomers believe such planets might be common in the galaxy. Planet formation is a chaotic process, and many planetary systems probably eject planets through gravitational interactions. These ejected planets wander through the galaxy as free-floating worlds. If one passed close to our solar system at just the right speed and angle, capture is theoretically possible. If Planet 9 is real and is in a high inclination orbit, it would be an extraordinary discovery. It would mean that our solar system's planetary architecture extends into the vertical dimensions in a way we never suspected. The planets wouldn't just be confined to a flat disk. There would be significant planetary mass in the sphere, orbiting high above or below the familiar plane. But we should be cautious. Planet 9 remains hypothetical. The orbital clustering that suggested its existence could potentially be explained by other mechanisms, or could even be an artifact of observational bias. Many astronomers are searching for Planet 9, scanning the skies in the regions where it's predicted to be, but so far, no one has found it. If it doesn't exist, that's also interesting. It would mean the outer solar system doesn't harbour any hidden large planets, that what we see is what we get. The vertical dimensions would still be populated by smaller objects, dwarf planets and comets and icy bodies, but no worlds massive enough to be called true planets. Either way, the question illustrates how much we still don't know about our own solar system. The possibility that there might be a planet several times Earth's mass hiding in the outer reaches, perhaps in the vertical dimensions above or below the ecliptic, is a humbling reminder of the limits of our observations and our knowledge. As we continue to survey the sky, using ever more sensitive instruments and more comprehensive search strategies, we'll gradually fill in the gaps. If Planet 9 is out there, we'll find it eventually. If it's not, we'll reach a point where we can confidently say that no such planet exists. But for now, the vertical dimensions of the outer solar system remain a place of possibility where major discoveries might still await. We've spoken about the Oort Cloud as the outermost region of the solar system, but there's another important boundary to consider: the heliopause. The edge of the Sun's influence measured not by gravity but by the solar wind. This boundary exists in all directions, including directly above and below the ecliptic plane, and its shape and location in these vertical dimensions is something we have only recently begun to understand. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the Sun at hundreds of kilometers per second. This wind fills the solar system, creating a bubble called the heliosphere. Inside this bubble, the solar wind dominates. Outside, the interstellar medium, the thin gas that fills the space between stars, takes over. The boundary between these two regions is the heliopause. It's not a solid surface, but rather a transition zone where the solar wind's pressure balances against the pressure of the interstellar medium. Beyond the heliopause, you're in interstellar space, no longer in the Sun's magnetic domain. In the ecliptic plane, where the solar wind is strongest and most focused, the heliopause is located at about 120 astronomical units from the Sun. We know this because Voyager 1 crossed the heliopause in this general region in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 crossed at a slightly different location and distance in 2018. But what about above and below the ecliptic plane? The solar wind isn't perfectly uniform. It's affected by the Sun's rotation, by magnetic field structure, by variations in solar activity. These effects create an asymmetry in the heliosphere. It's not a perfect sphere. It's more like a squashed sphere or even a bullet shape, with a blunt nose in the direction the Sun is moving through the interstellar medium and a long tail trailing behind. Models suggest that in the polar directions, straight up and down from the Sun's poles perpendicular to the ecliptic, the heliopause might be at a different distance than in the ecliptic plane. Some models predict it's farther away in the polar directions, perhaps 150 astronomical units or more. Others suggest it might be closer, depending on the properties of the interstellar magnetic field and the solar wind. We don't know for certain because we haven't sent a spacecraft through the heliopause in the polar directions. Voyager 1 and 2 are both travelling at modest angles to the ecliptic plane, not straight up or down. New Horizons, which flew past Pluto in 2015 and is now heading outward, is also not on a polar trajectory. There's a proposed mission concept called the Interstellar Probe that would specifically target the heliopause and beyond, with the goal of studying the heliosphere's structure and the nearby interstellar medium. This mission would likely be designed to travel at high inclination, specifically to study the polar regions of the heliosphere and cross the heliopause far from the ecliptic plane. If such a mission is ever flown, it would give us our first direct measurements of conditions in the vertical dimensions at the edge of the solar system. It would tell us where the heliopause is located above or below the Sun, how solar wind properties vary with latitude, and what the interstellar medium looks like in these directions. Why does the heliopause matter for our understanding of the vertical dimensions? Because it represents a different kind of boundary than the gravitational edge of the Oort Cloud. The Oort Cloud extends to perhaps 100,000 astronomical units, far beyond the heliopause. So there's a region from about 150 astronomical units to 100,000 astronomical units, where objects are still gravitationally bound to the Sun but are in interstellar space in terms of the plasma environment. An object in this region would be outside the heliosphere, bathed in the interstellar medium, exposed to galactic cosmic rays at full intensity, without the shielding of the Sun's magnetic field. Yet it would still be orbiting the Sun, still part of the solar system gravitationally. This is true in all directions, but it's particularly interesting in the vertical dimensions, because those are the directions we've explored least. We have some sense of conditions along the Voyager's trajectories, which are roughly in the ecliptic plane or at modest angles to it, but straight up or down, those are genuine unknowns. The interstellar medium itself might be different in different directions. The Sun is moving through the interstellar medium at about 26 kilometers per second, relative to the local cloud of gas in which we're embedded. This creates a headwind of interstellar material in the direction of the Sun's motion, and _7_ in the opposite direction. But perpendicular to the Sun's motion, including the polar directions, the interstellar medium might have different properties. There are also large-scale structures in the interstellar medium, regions called the local bubble and the local fluff, which have different densities and temperatures. Our solar system is currently inside the local fluff, a small cloud of warm gas. But the local bubble, a region of very low density carved out by ancient supernovae, extends around us. The properties of the interstellar medium in the vertical directions might reflect these larger structures. All of this affects conditions for any objects in the vertical dimensions at the solar system's edge. Are they in a denser or thinner part of the interstellar medium? Are they exposed to more or fewer cosmic rays? Is the galactic magnetic field stronger or weaker in their location? These factors could influence their long-term evolution, their surface chemistry, their potential for acquiring mantles of interstellar ice or dust. We're only beginning to appreciate the complexity of the solar system's edge, the realization that it's not a simple, uniform boundary, but a complex, variable transition shaped by the interaction between the Sun's influence and the interstellar environment. And in the vertical dimensions, much of this complexity remains unexplored, waiting for future missions and observations to reveal it. The orbits we observe in the vertical dimensions of the outer solar system aren't just current snapshots. They're also historical records, preserving information about events that happened billions of years ago. By studying the distribution of inclinations and orbital orientations, astronomers can infer things about the solar system's past, about stellar encounters and dynamical upheavals that shape the structure we see today. One of the most significant events in the early solar system was the migration of the giant planets. There's strong evidence that Jupiter, Saturn, Uranus, and Neptune didn't form where they are now. Instead, they formed closer together and closer to the Sun, and then migrated outward over time due to gravitational interactions with the disk of planetesimals that surrounded them. This migration wasn't smooth. Models suggest there was a period, perhaps several 100 million years after the solar system's formation, when the planets' orbits became unstable. Jupiter and Saturn crossed a resonance, a configuration where their orbital periods had a simple ratio. This triggered a dynamical instability that scattered Uranus and Neptune outward, sent countless planetesimals into the inner solar system, causing the late heavy bombardment that cratered the Moon, and reshaped the outer solar system. This event, sometimes called the Late Heavy Bombardment, or associated with the Nice model, named after the French city where the model was developed, would have had profound effects on the vertical distribution of objects in the outer solar system. Planetesimals scattered by the migrating planets could have been flung into highly inclined orbits. Some would have been ejected from the solar system entirely. Others ended up in the scattered disk or the Oort Cloud. The signature of this event might still be visible in the inclination distribution of scattered disk objects and inner Oort Cloud objects. If these populations show certain patterns in their inclinations and orbital orientations, it could be evidence of the scattering event. Astronomers are actively studying this, comparing observations to computer simulations to test whether the Nice model or its variants can explain what we see. But planetary migration isn't the only ancient event recorded in vertical orbits. Stellar encounters early in the solar system's history also left their mark. The Sun formed in a stellar cluster, surrounded by hundreds or thousands of sibling stars. In such a dense environment, close stellar encounters were probably common. A star passing within a few thousand astronomical units of the young Sun could have dramatically perturbed the outer regions of the protoplanetary disk and the nascent Oort Cloud. It could have stripped away some material entirely, stolen it into an orbit around the passing star or into interstellar space. It could have excited the inclinations and eccentricities of the remaining material, creating the vertical structure we observe today. There's even a hypothesis that a specific stellar encounter early in the solar system's history could explain some otherwise puzzling features. For example, the detached objects like Sedna have orbits that are hard to explain through interactions with the known planets alone. A stellar encounter could potentially account for these orbits. If a star passed close enough, say 1,000 to 2,000 astronomical units from the Sun, it could have torqued Sedna's orbit, lifting its perihelion and increasing its inclination. The passing star would have long since moved on, now far away in the galaxy, but its gravitational handshake with our solar system would be frozen in Sedna's orbit, a fossil record of an encounter billions of years ago. Another possibility that's been considered is that the Sun might have had a binary companion early in its history, another star in a close orbit. Such a companion could have shaped the early Oort Cloud, creating structure and affecting inclinations. If this companion was later stripped away, perhaps by gravitational interactions within the birth cluster, or by a close encounter with another star, it would leave behind orbital signatures that we might still detect. These ideas are speculative, but they illustrate how the vertical dimensions of the solar system can serve as an archive. Every high inclination orbit is a clue, a piece of data that constrains models of solar system history. By collecting enough of these clues, by mapping the three-dimensional structure of the outer solar system in detail, we can work backward to infer what events shaped it. It's like archaeology, but instead of digging through layers of soil to uncover artifacts, we're cataloguing orbits to uncover dynamical events. Each orbit is an artifact shaped by the forces that acted on it. The challenge is to read these artifacts correctly, to interpret the patterns we see in terms of the processes that created them. This work is ongoing. Every new discovery of a high inclination object, every refinement in our census of the outer solar system adds to the data set. Computer simulations become more sophisticated, testing different formation and evolution scenarios. Slowly, we're converging on a better understanding of solar system history, and it's worth noting that this history isn't over. The solar system continues to evolve. Future stellar encounters will perturb the Oort Cloud further, send new comets falling inward, perhaps strip away more material or impart new structure. The galactic tide continues to act, slowly reshaping orbits. The vertical dimensions of the outer solar system are still being sculpted, still changing, albeit on timescales so long that human lifetimes are irrelevant. When we observe the current state of these regions, we're seeing one frame from a billions of years-long movie. The past is recorded in the distribution we observe, and the future is being written by the slow action of gravitational forces. It's a dynamic, evolving system, and our glimpse of it is just a moment in deep time. In the vertical dimensions of the Oort Cloud, far from the Sun's heat, chemistry takes on a character very different from what we're familiar with on Earth, or even in the inner solar system. The extreme cold, the absence of liquid water, the feeble sunlight. All these create conditions where unusual chemical processes can occur, or where terrestrial chemistry is frozen into stasis. Let's start with the basics of what these distant objects are made of. The consensus is that Oort Cloud objects like Kuiper Belt objects and comets are primarily composed of ices, water ice, carbon dioxide ice, methane ice, ammonia ice, and various other frozen volatiles. Mixed with these ices are rocky dust grains, silicates and organics left over from the molecular cloud that collapsed to form the solar system. At 3 Kelvin, the temperature in the outer Oort Cloud, these ices are frozen solid in forms that might be unfamiliar. Water ice, for example, can exist in multiple crystalline forms depending on temperature and pressure. At very low temperatures, it tends to form what's called amorphous ice. a disordered structure more like glass than crystal. This amorphous ice is extremely cold and hard, and it can trap other molecules within it. Methane, ammonia, and other small molecules might be trapped in the matrix of the water ice, or they might form their own pure ices on the surface or in pockets. Carbon dioxide can form dry ice, just like on Mars, but even colder. More complex organic molecules. Things like formaldehyde, methanol, ethane, and various nitriles and hydrocarbons might be present in small amounts. What's fascinating is that chemistry doesn't completely stop at these low temperatures. It's drastically slowed, but certain reactions can still occur, driven by radiation rather than heat. Cosmic rays, high-energy particles from outside the solar system, constantly bombard the surfaces of Oort Cloud objects. When a cosmic ray strikes an ice, it can break chemical bonds, creating free radicals and ions. These free radicals can then slowly react with neighbouring molecules, creating new compounds. Over millions of years, this radiolysis can build up complex organic molecules, even in the absence of heat or liquid water. It's a form of chemistry driven purely by radiation, creating a slow but steady synthesis of more complex compounds from simpler starting materials. There's also photochemistry, driven by the faint ultraviolet light from stars. Even though the sun is distant and faint, it and other stars emit UV light that can reach Oort Cloud objects. UV photons can also break bonds and drive chemical reactions. Again, the rates are extremely slow at 3 Kelvin, but given enough time, significant changes can accumulate. Some scientists have speculated that the surfaces of Oort Cloud objects might be coated with a layer of complex organic material, a kind of radiation-processed tar made from simpler ices. This layer might be dark, which would make the objects harder to detect since they'd reflect less light. It might also preserve information about the original ice composition underneath, like a protective blanket. When one of these objects falls into the inner solar system and becomes a comet, its surface chemistry is suddenly exposed to much more intense radiation and heat. The ices begin to sublimate, and the pristine surface material that's been frozen for billions of years is vaporized and ejected into space. Instruments on Earth or on spacecraft can analyze this ejected material, giving us a glimpse of the chemistry that occurred in the Oort Cloud. Comets have been found to contain a surprising diversity of organic molecules, including things like formaldehyde, methanol, ethanol, glycolaldehyde, a sugar-related molecule, and even amino acids, the building blocks of proteins. Some of these molecules might have been present in the original material from which the solar system formed, but others might have been created by radiolysis and photochemistry during the comet's billions of years in the Oort Cloud. This raises an intriguing possibility. The Oort Cloud might be a vast chemical laboratory, slowly synthesizing complex organic molecules through radiation-driven processes. When comets from the Oort Cloud fall into the inner solar system and impact planets, they could be delivering these organic molecules, seeding planets with the chemical ingredients for life. Earth, in its early history, was bombarded by comets and asteroids, and some of the organic material necessary for the origin of life might have been delivered this way. If so, the chemistry of the Oort Cloud, occurring in the cold heights and depths far from the sun, might have played a crucial role in making Earth habitable and in enabling the emergence of life. There's also the possibility of more exotic chemistry. At very low temperatures, quantum effects can become important. Tunneling, where particles pass through energy barriers that would be insurmountable classically, might allow reactions to occur that wouldn't happen at higher temperatures. Certain isotopic fractionation processes might operate differently. The physics of low-temperature chemistry is complex and not fully understood. Studying this chemistry is challenging because we can't easily access Oort Cloud objects directly. We're limited to analysing comets that have fallen inward, and by the time they reach us, they've been altered by their passage through the inner solar system. The pristine surface chemistry has been modified by heating and outgassing. What we really need is a sample return mission to the Oort Cloud, a spacecraft that could rendezvous with an object still in the cold, study it in situ, and perhaps return samples to Earth for detailed analysis. Such a mission is far beyond current capabilities, but it's not impossible in principle. If we develop faster propulsion systems, perhaps nuclear-powered or even antimatter-powered spacecraft, reaching the Oort Cloud might become feasible within a human lifetime. Until then, we're left to infer the chemistry of these distant regions from computer models, from laboratory experiments that simulate Oort Cloud conditions, and from the analysis of comets. It's detective work, piecing together clues to understand a realm we've never visited. But slowly, the picture is becoming clearer, and what we're learning is that even in the cold, dark, vertical dimensions at the edge of the solar system, chemistry is active, slowly transforming matter in ways we're only beginning to appreciate. Let's imagine, just as a thought experiment, what it would be like to take a journey straight up from the ecliptic plane, leaving the disk of the planets behind and travelling vertically through the solar system's outer dimensions. It's a journey no human will make in our lifetimes, but perhaps in imagining it, we can better understand the structure we've been exploring. We start at Earth's orbit, 1 astronomical unit from the Sun. Around us is the familiar realm of the inner solar system, the Sun blazing in the sky, the inner planets visible at various times. We're in the ecliptic plane, the disk where most of the action happens. Now we begin to move perpendicular to this plane, straight up in the direction of the north ecliptic pole. At first, not much changes. We're still well within the orbits of the planets. At 10 astronomical units, about the distance to Saturn, we'd be only slightly north of Saturn's orbital plane, but we'd start to get a different perspective. Looking back at the Sun and planets, we'd see them starting to separate in our view. The inner planets would cluster close to the Sun, while the outer planets would be spread around their orbits. At 30 astronomical units, Neptune's distance, we've passed beyond the last major planet if we measure radially from the Sun, but we're now about 5 astronomical units above the ecliptic plane, so we're actually farther from Neptune than 30 astronomical units. Looking back, the planetary orbits would appear as a flat disk, and we could see the disk edge on, a thin line of planetary motion against the background stars. Continuing upward, we enter the realm of the Kuiper Belt. Even though we're now well above the main concentration of the belt, we'd still encounter objects in high inclination orbits. At 50 astronomical units and 10 astronomical units above the plane, we might spot a few distant Kuiper Belt objects if we had a good telescope. They'd appear as faint points of light moving slowly against the stars. At 100 astronomical units, about the distance of the heliopause in the ecliptic plane, we're now about 17 astronomical units above the plane. We cross the heliopause, exiting the Sun's magnetic domain and entering interstellar space in terms of plasma environment. Though we're still gravitationally bound to the Sun, the solar wind disappears, replaced by the thin, neutral gas of the interstellar medium. Cosmic ray intensity increases slightly as we leave the heliosphere's shielding. Pushing further to 1,000 astronomical units, we're now 173 astronomical units above the ecliptic plane. This is deep in the scattered disk or early Oort Cloud territory. The Sun is still the brightest star in the sky, but it no longer looks like a disk. It's a brilliant point of light, brighter than Venus appears from Earth, but still just a star. Looking back at the solar system from here, we'd have a unique view. The planetary disk would be far below us, visible edge on. We might be able to track the giant planets in their orbits if we watched patiently enough and had instruments sensitive enough. The inner planets would be lost in the Sun's glare, invisible even with good optics because of the brightness difference. At 10,000 astronomical units, we're 1,700 astronomical units above the plane, well into the inner Oort Cloud. The Sun is now just one star among many, still the brightest from our location, but not overwhelmingly so. Sirius, Alpha Centauri, and other nearby bright stars are visible, and the Sun is comparable to them in apparent brightness. The solar system below is invisible to the naked eye. We'd need instruments to detect it at all. The Milky Way stretches across the sky, a band of light from billions of distant stars. We're still within the galaxy, of course, but we're seeing it from a slightly different vantage than from Earth. The constellations are unchanged. We haven't travelled far enough to see parallax shifts in the stars. But our perspective on the solar system is completely transformed. At 50,000 astronomical units, or 8,600 astronomical units above the ecliptic approaching the outer regions of the Oort Cloud, the Sun is now much fainter, roughly the same brightness as the brighter stars but no longer special. If we didn't know which star was the Sun, we might have trouble picking it out from the others. The temperature has dropped to about 3 Kelvin, set by the cosmic microwave background rather than by sunlight. Any ship we're travelling in would need active heating to remain warm. Solar panels would be useless. We'd need nuclear power or some other energy source. Looking around, we'd see other Oort Cloud objects if we were lucky and had excellent instruments. But space is vast even here. The average separation between objects might be billions of kilometres. We could travel for years without passing close to another object. Finally, at 100,000 astronomical units, nearly 17,000 astronomical units above the ecliptic plane, and about 1.5 light years from the Sun, we've reached the edge of the solar system's gravitational domain. Beyond here, the Sun can't hold onto objects. The galactic tide and the gravity of other stars dominate. From this ultimate height, the solar system is a distant memory. The Sun is merely one star in a sky full of stars. The planets, even the giant planets, are completely invisible, lost in the distance and the Sun's glare. Earth, our starting point, is utterly undetectable, a mote of dust circling a mediocre star. And yet, we're still connected. If we turned around and fell back toward the Sun, accelerated by gravity, we'd eventually return to the inner solar system. We're in an incredibly elongated orbit, but it's still an orbit. The Sun's gravity, weak as it is here, still has us in its grasp. This thought experiment illustrates the vertical extent of the solar system. The journey from the ecliptic plane to the edge takes us through every regime we've discussed. The planetary disk, the Kuiper Belt's thickness, the scattered disk, the transition zone, the inner and outer Oort Cloud, and finally to the boundary of interstellar space. It's a journey of distances almost beyond human comprehension. At our current spacecraft speeds, it would take hundreds of thousands of years. Even with dramatic improvements in propulsion, reaching the outer Oort Cloud would require travel times measured in decades or centuries. But perhaps someday, our descendants will make such journeys. Perhaps future civilizations, if humanity survives and flourishes, will explore these vertical dimensions directly, sending expeditions to study the Oort Cloud in situ, to sample objects at various distances and inclinations, to map the three-dimensional structure we currently can only infer. If that day comes, those explorers will confirm or refute the models we've built. They'll discover whether the Oort Cloud is really as we imagine it, or whether it holds surprises we haven't anticipated. They'll learn the true chemistry of these cold objects, the true distribution of sizes and compositions, the true history written in their orbits. Until then, we can only imagine, extrapolating from our limited data, constructing our mental pictures of these vast and lonely reaches. But the imagining itself is valuable. It expands our perspective, reminds us of the scale of the system we inhabit, and humbles us with the knowledge of how much remains unknown. Throughout this exploration, we've been describing things that, for the most part, have never been directly observed. The Oort Cloud, the population of high-inclination objects in the scattered disk, the detailed structure of the vertical dimensions, these are all inferred rather than seen. It's worth pausing to contemplate what that means, to appreciate the nature of knowledge that rests on inference rather than direct observation. We know the Oort Cloud exists because of the orbits of long-period comets. These comets come from all directions, from above and below the ecliptic, from all sides. They arrive with orbital energies that indicate they came from vast distances, tens of thousands of astronomical units. When we trace their orbits backward, they lead to a spherical shell surrounding the solar system. This is powerful evidence, but it's circumstantial. We've never actually seen an object still in the Oort Cloud. Similarly, we infer the existence of populations of high-inclination objects in the scattered disk and beyond from the handful of examples we've discovered. Each discovery of an object like Sedna or Eris tells us that such objects exist and hints at larger populations we haven't found yet. But our census is incomplete, perhaps drastically so. We're seeing the tip of the iceberg and inferring the rest. This kind of inference is common in astronomy. We can't visit distant stars to confirm they exist, yet we trust that the points of light in the sky are real stellar objects because the evidence is consistent and overwhelming. We can't dig beneath the surfaces of other planets except in very limited ways, yet we build models of their interiors based on gravitational fields, seismic data, and our understanding of physics. The vertical dimensions of the solar system are like that. We have pieces of evidence, a few high-inclination orbits here, theoretical calculations there, computer simulations that reproduce certain features. We weave these together into a coherent picture, a model of what exists above and below the ecliptic plane. But models can be wrong. History is full of examples where astronomers constructed elaborate models that turned out to be incorrect when better observations became available. The question is, how confident should we be in our picture of the solar system's vertical structure? Fairly confident, actually, for some aspects. The basic existence of the Oort Cloud as a spherical reservoir of comets seems secure. The evidence from long-period comet orbits is strong and consistent. The theoretical basis, the idea that the early solar system scattered planetesimals into distant orbits that were then sphericalized by external perturbations, makes sense and is supported by detailed simulations. For other aspects, we should be more cautious. The exact distribution of objects with distance and inclination, the total mass of the Oort Cloud, the dividing line between the inner and outer cloud, these are more uncertain. Different models give different answers, and we don't yet have observations to distinguish between them definitively. There could also be complete surprises waiting. Perhaps there are populations of objects we haven't predicted at all. Perhaps the structure is more complex than our models suggest, with concentrations or voids at certain distances or inclinations. Perhaps the composition varies in unexpected ways, or the size distribution is different than we assume. This uncertainty is both frustrating and exciting. Frustrating because we'd like to know the answers, to have a complete and accurate picture of our own solar system. But exciting because it means there's still discovery to be done, still the potential for surprises that will revise our understanding. Every new discovery in the outer solar system, every new high-inclination object, every refinement in comet orbit statistics brings us closer to truth. It's a gradual process, an accumulation of evidence that slowly constrains the models and narrows the range of possibilities. There's also something philosophically interesting about knowledge based on inference. It reminds us that much of what we know about the universe isn't from direct experience, but from reasoning, from taking what we can observe and extrapolating to what we cannot. This is the essence of science. Building models, making predictions, testing them against observation, and refining understanding. In a sense, the vertical dimensions of the solar system are a perfect example of this process in action. We've built a picture of these regions from fragments of evidence and chains of reasoning. We're fairly sure the picture is mostly correct, but we acknowledge it might have errors or gaps, and we continue to observe, to refine, to test, gradually transforming inference into certainty. One day, perhaps, direct observation will replace inference. A spacecraft might visit the Oort Cloud, or advanced telescopes might detect objects still in their distant orbits. When that happens, we'll compare our models to reality and learn where we were right and where we were wrong. Until then, the vertical dimensions remain a place of inference, a region we've mapped with minds rather than instruments. It's a testament to human ingenuity that we can do this at all, that from our vantage point on a small planet we can deduce the structure of regions billions of kilometres away that we've never seen. It's also a reminder of our limitations, that there are still blank spaces on the map, places where our knowledge fades into educated guessing. As we near the end of our exploration, it's worth broadening our perspective to consider whether other solar systems have vertical dimensions similar to ours. Do other stars have their own Oort clouds? Do exoplanets orbit in high inclination paths above and below their system's ecliptic? What might we learn by comparing our solar system's vertical structure to that of other planetary systems? The answer is that we're only just beginning to explore these questions. Detecting exoplanets, planets orbiting other stars, is difficult enough when they orbit in the plane we can observe most easily. Detecting objects in high inclination orbits, or inferring the existence of Oort Cloud analogues around other stars, is far more challenging. For exoplanets, our detection methods have biases. The transit method, where we detect a planet by the slight dimming of its star as the planet passes in front, only works for planets whose orbits are nearly edge-on to our line of sight. If a planet's orbit is highly inclined relative to our viewing angle, we won't see transits. The radial velocity method, where we detect a planet by the wobble it induces in its star's motion, is most sensitive to planets in the plane perpendicular to our line of sight. Despite these biases, we've found some exoplanets in high inclination orbits. Some systems have planets whose orbital planes are tilted relative to their star's equatorial plane, sometimes dramatically so. There are even planets in retrograde orbits, orbiting opposite to their star's rotation. These misalignments tell us that planetary systems can have complex vertical structures. What causes these misalignments? Several mechanisms have been proposed. Gravitational interactions with other planets in the system can tilt orbits. Interactions with a binary companion star can torque planetary orbits. Passage through a stellar cluster early in the system's history could perturb orbits. In some cases, planets might have formed in a disk that was already tilted relative to the star's equator. As for Oort Cloud analogues, we have only indirect evidence. Some stars show excess infrared emission that might come from dust produced by collisions in a distant icy reservoir, analogous to our Oort Cloud. Observations of debris disks around other stars sometimes show vertical thickness or warps that could indicate populations of objects at various inclinations. There's also theoretical work suggesting that Oort clouds should be common. The process that created our Oort cloud, scattering of planetesimals by giant planets, followed by external perturbations that sphericalize the distribution, should occur in other planetary systems too. Any star with giant planets and a birth in a stellar cluster should end up with an Oort cloud of some kind. The properties might vary though. A star that formed in a denser cluster might have had more stellar encounters, leading to a more compact or more stripped Oort cloud. A star with more massive planets might have scattered more material outward, creating a more populous cloud. A star that formed in isolation might have a more disk-like outer reservoir, lacking the stellar encounters needed to fully sphericalize it. Interestingly, the study of exoplanet systems has revealed that our solar system might be somewhat unusual. Many exoplanetary systems are more compact, with multiple planets orbiting closer to their star than Mercury orbits the Sun. Some have hot Jupiters, giant planets on very tight orbits. These configurations don't look like our system at all. As our observational capabilities improve, we'll learn more about the vertical dimensions of other planetary systems. Future telescopes, both ground-based and space-based, will be able to detect fainter objects and measure orbits more precisely. We'll start to census high-inclination planets, and perhaps even detect signatures of Oort cloud analogues. There's also the possibility of directly imaging debris or planets in the vertical dimensions of nearby systems. With advanced adaptive optics and coronagraphs, we might be able to block out the light of a star and see faint objects orbiting around it, even in high inclination orbits. What would we learn from such comparative studies? We'd gain insight into how common our solar system's architecture is. If most systems have Oort clouds and high inclination populations, it would suggest these features are robust outcomes of planet formation. If they're rare, it would mean our solar system's history was somehow special. We'd also learn about the processes that shape vertical structure. By seeing systems at different stages of evolution, in different galactic environments, with different planetary configurations, we better understand how vertical dimensions form and evolve. And perhaps we'd find systems with vertical structures very different from ours, configurations we haven't imagined yet. The universe has a way of surprising us, of producing phenomena that our theories didn't predict. The vertical dimensions of other solar systems might hold such surprises. For now, though, we can only speculate. Our most detailed knowledge remains confined to our own solar system. The vertical dimensions we've explored tonight are the ones we're most familiar with, even if we've never directly observed most of them. As we extend our observations outward to other stars, we'll gradually build a comparative picture, understanding the solar system not in isolation, but as one example of a broader phenomenon. Let's take a moment to imagine what the solar system looks like from far above or below the ecliptic plane. Not from within it, as we normally experience, but from a distant vantage point in the vertical dimensions, looking at the entire system from the outside. Imagine you're at a position 50,000 astronomical units above the north ecliptic pole, looking down at the solar system below. What would you see? First, you'd see the sun, a bright star, not the brightest in the sky from your location, but certainly noticeable. Around the sun, in a very flat disk that from your vantage point looks almost like a straight line, are the planets. They're so close to the sun compared to your distance that you'd barely be able to resolve them as separate objects. The entire planetary system, from Mercury to Neptune, fits within a circle just 60 astronomical units across. From 50,000 astronomical units away, that's a tiny angle. If you had a good telescope, you could track the planets in their orbits. You'd see Jupiter completing an orbit every 12 years, Saturn every 29 years, the inner planets moving much faster. The motion would be stately, slow, like watching a clockwork mechanism from a great distance. But what would really stand out is the spherical structure around the sun. From your high vantage point, you'd have a unique perspective on the Oort Cloud. Looking down, you'd see it extending below the ecliptic plane just as it extends above. Looking to the sides, you'd see it surrounding the sun in all directions. You'd perceive the solar system not as a disk, but as a sphere, with the disk as just a thin, almost negligible feature at the very centre. If you could somehow see the individual Oort Cloud objects, which you couldn't with realistic instruments, but let's imagine, you'd see them as a sparse cloud of points thinning out with distance from the sun. Near the inner edge of the cloud, a few thousand astronomical units from the sun, they'd be somewhat denser. Farther out, approaching the outer edge, they'd be sparser, but in all directions the distribution would look roughly the same. There'd be no concentration in the ecliptic plane from your perspective. Until that day, we can only imagine this view, constructing it in our minds from the data and models we have. But the imagining is worthwhile. It shifts our perspective, helps us see the solar system not as a flat diagram, but as a real, three-dimensional structure embedded in space. And it reminds us that perspective matters. From Earth, looking out along the ecliptic, the solar system appears one way, from above or below. It appears very different. Neither view is wrong, they're just different perspectives on the same reality. The full truth encompasses both, and more besides, all the possible viewpoints from all the possible vantage points throughout the system and beyond. There's something profoundly moving about contemplating the objects in the vertical dimensions of the outer solar system, the ones in the Oort Cloud and the scattered disk, orbiting in the darkness far from the sun. These are perhaps the loneliest objects in the solar system, separated from the warmth and light that we take for granted, drifting in cold silence for billions of years. Imagine being an observer on one of these objects. If such a thing were possible, you'd be alone in a way that's hard for humans to comprehend. The sun would be just a bright star, no longer providing meaningful heat. You'd be surrounded by darkness, broken only by the light of distant stars and the faint glow of the cosmic microwave background. There would be no day or night in the way we experience them. The sun wouldn't rise or set. It would hang in the sky at a nearly fixed position, barely moving over the course of years. If your object rotates, you'd experience a kind of day/night cycle as the sun appeared and disappeared, but it would be a cycle of dim light and dimmer darkness, not the dramatic contrast we know on Earth. Time would feel different, stretched out. Your orbital period might be millions of years. In a human lifetime, you'd move an imperceptible fraction of your orbit. You'd see the same stars in the same positions your entire life. The universe would seem frozen, unchanging. And yet, on a longer timescale, things would change. Over thousands of years, the stars would slowly shift their positions due to their proper motions. Over millions of years, stellar encounters might perturb your orbit, sending you on a new path. The isolation isn't permanent. It's just patient, measured in timescales that dwarf human comprehension. As we contemplate these distant objects, these lonely wanderers in the vertical dimensions of the solar system, we might feel a sense of melancholy, but also a sense of wonder. They're out there right now, orbiting in the darkness, just as they have for billions of years and just as they will for billions more. They don't know we exist, and they don't care, but we know they exist, and in knowing, we're connected to them across the vast gulf of space. After our long journey through the vertical dimensions, up through the heights and depths of the solar system, it's time to bring our perspective back to the familiar disk, to the ecliptic plane where the planets orbit and where we ourselves reside. There's something satisfying about this return, a sense of coming home after a long voyage. From our elevated perspective, looking down from the Oort Cloud or from some imagined vantage point high above the solar system, the disk appears small and fragile. All the planets we can see from Earth, all the asteroids and comets that populate the inner solar system, all the human activity and history, it's all confined to this thin layer, this slice through space barely 60 astronomical units across, and only a few astronomical units thick. And yet, this thin slice is where the action is. This is where the sun's heat and light are strong enough to warm surfaces, to drive weather, to create the conditions for liquid water, and possibly for life. This is where gravitational interactions between planets are strong and frequent, where orbits are crowded, where things happen on timescales we can observe. The vertical dimensions we've explored are important, vast, full of material and history, but they're also quiet, slow, patient. The disk is where the drama unfolds, where change happens, where complexity arises. In a sense, the disk and the sphere complement each other. The sphere provides the context, the reservoir, the long-term memory. The disk provides the activity, the evolution, the present moment. Earth itself, our home, is a tiny part of this disk. We orbit at 1 astronomical unit, in the middle range of distances where planets exist. We're tilted slightly relative to the ecliptic plane by about 23.5 degrees, which gives us seasons as different hemispheres tilt toward or away from the sun over the course of a year. But this tilt is measured relative to our own orbital plane, not relative to the ecliptic itself. Earth's orbital plane is the ecliptic by definition. Looking out from Earth at the night sky, we see the solar system primarily in projection onto the celestial sphere. The planets wander along the ecliptic, that same narrow band where the sun appears to move. The moon orbits close to the ecliptic too, crossing it twice per orbit, which is when eclipses can occur. Everything visible to the naked eye in the solar system stays within a few degrees of this line across the sky. But now, after our exploration, we understand that this is just one view. If we could see in different wavelengths, or if we had instruments sensitive enough to detect the faint light from distant objects, we'd see that the solar system extends far beyond this narrow band. Objects in high inclination orbits appear all over the sky, not just near the ecliptic. The Oort Cloud surrounds us in all directions, though invisibly. This dual nature of the solar system, disk and sphere, is worth appreciating. We live in the disk, but we're surrounded by the sphere. Our perspective is inherently limited, but our minds can comprehend the full three-dimensional structure. We're part of a system that's both flat and volumetric, both simple and complex. There's also something humbling about returning to the disk after contemplating the vertical dimensions. All of human history, every civilization that's risen and fallen, every war fought and peace made, every work of art created and scientific discovery achieved, all of it happened in this thin disk, on one small planet orbiting in this plane. The vast vertical dimensions existed throughout, indifferent to our dramas, continuing their slow dance around the sun. And yet, we've reached a point where we can understand these vertical dimensions even though we've never visited them. We've used mathematics and physics, observation and inference to map regions of space that no human has seen directly. That's a remarkable achievement, a testament to the power of the human mind to transcend its limitations. As we settle back into our familiar perspective, looking out from Earth along the ecliptic, we might see the sky differently now. That blank space between the planets, the dark regions above and below the plane where no bright objects reside, those aren't empty. They're full of distant, invisible objects. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. They're full of distant, invisible objects, part of our solar system but hidden from casual view. The comets we occasionally see, developing their tails and becoming bright enough for naked eye observation, many of them fell from these vertical dimensions, plunging down from the Oort Cloud toward the sun. They're messengers from the heights and depths, visitors from the sphere dropping into the disk for a brief, dramatic appearance before returning to the darkness. Perhaps there's a metaphor here about perspective and understanding. From within the disk, focused on the bright nearby objects, it's easy to think that's all there is. But if we step back, if we think three-dimensionally, we realise there's so much more. The visible is just a tiny fraction of the real. The familiar is just one aspect of a larger, more complex truth. This applies not just to the solar system, but to many aspects of existence. What we see directly is limited by our position, our perspective, our instruments. But by thinking carefully, by making inferences, by building models and testing them, we can understand things beyond our immediate perception. We can map the invisible, comprehend the distant, know the unknowable. As we bring our journey to a close, returning fully to our home planet and our familiar view of the sky, let's carry with us the expanded understanding we've gained. The solar system isn't just the disk we see. It's also the vast sphere we've explored tonight, the vertical dimensions above and below, the cold heights and depths where lonely objects orbit in the darkness. All of it together, disk and sphere, near and far, bright and invisible, that's the true solar system. That's the system we inhabit, the cosmic context of our existence. And knowing this, truly understanding it, changes how we see the sky, and perhaps how we see ourselves. We've travelled together tonight through 150 minutes, 2.5 hours of slow drift through the vertical dimensions of the solar system. From the ecliptic plane where we began, up through the Kuiper Belt's gentle arc, past the scattered disk objects in their inclined orbits, through the transition zone where disk becomes sphere, and out into the vast Oort Cloud that surrounds everything in a great sphere of ice and rock. We've contemplated distances that dwarf human experience, timescales that stretch across billions of years, objects that exist in cold and darkness beyond our ability to easily imagine. We've asked questions about what exists above and below our solar system, and we've found that the answer is vast, complex, and in many ways still mysterious. From the question of whether there might be undiscovered planets in vertical orbits, to the chemistry occurring on the surfaces of Oort Cloud objects, from the history written in ancient orbital inclinations to the perspective we might gain by viewing the solar system from high above, we've explored dimensions of our cosmic neighbourhood that are rarely discussed, rarely visualised, but always present. The answer, as honestly as I can give it, is that above and below our solar system lies the bulk of the solar system itself. The disk we're familiar with, the plane of the planets, is just the active heart of a much larger system. The vertical dimensions contain most of the volume, perhaps most of the mass in the form of countless icy bodies, and certainly most of the spatial extent reaching out to nearly 100,000 astronomical units above and below the ecliptic plane. These vertical reaches are dynamic, not static. Objects slowly migrate between inclinations. Orbits evolve under the influence of external perturbations, comets fall inward from the heights, bringing messages from the ancient past. The solar system in its full three-dimensional glory is a living system, always changing, always evolving. Even if the timescales are so long that human lifetimes capture only the tiniest fraction of the motion. Perhaps the most important thing we've learned is that there's no sharp divide between quote 9 and quote 10. The solar system is three-dimensional, extending equally in all directions from the sun. The vertical isn't some exotic frontier. It's half of reality, the half we tend to forget because most of the bright objects stay near the ecliptic. If you enjoyed this slow drift through the less travelled dimensions of our cosmic neighbourhood, a like and subscribe genuinely helps others find these calm explorations. If you have thoughts about what we've discussed tonight, or questions about the vertical dimensions, the comments are always open for conversation. And to those of you who've been here with me for previous journeys through space and time, thank you. Your presence makes this work meaningful. Wherever you are in the world, I hope you're comfortable now. I hope your breathing has slowed to a gentle rhythm. I hope the concerns of the day have faded, replaced by the peaceful contemplation of distant ice and ancient orbits. I hope your body feels heavy and warm, ready for rest, ready for the gentle slide into sleep. Look up at the night sky, if you can, or imagine it if you can't. Picture not just the visible stars and planets, but the invisible architecture we've explored tonight. Above the plane of the planets, extending upward in the direction of the north ecliptic pole, there are objects, distant objects, orbiting in the darkness. Below, in the opposite direction, the same is true. All around Earth, in every direction, the Oort Cloud stretches outward, a vast sphere of icy worlds we'll likely never see, but which are just as real as the ground beneath your feet. All those distant objects, all those lonely chunks of ice and rock, they've been there for 4.5 billion years, and they'll be there for billions more. They watched the Earth form, watched life emerge, watched everything that's ever happened on our planet from a perspective so distant that Earth is invisible to them, lost in the sun's glare. They're timeless, patient, enduring. And yet they're part of our story. The water you drank today might have been delivered to Earth by a comet from the Oort Cloud. The organic molecules that made your body possible might have formed in the cold of the outer solar system and been brought here in an ancient impact. We're connected to these distant objects, kin to them across the vastness of space and time. Let that thought settle gently as you drift towards sleep. You're part of something larger, something that extends from the surface of the planet where you rest all the way to the furthest reaches of the solar system, 100,000 astronomical units above and below the familiar plane. The vertical dimensions are part of your home, even if you'll never visit them. Sleep well. Dream of dark ice slowly orbiting under starlight, of comets falling inward from the heights, of the vast and patient sphere that surrounds the bright disk where we live. Dream of the solar system in its full glory, disk and sphere together, all the dimensions visible and invisible, and when you wake, remember that when you look up at the night sky, you're not just seeing the stars, you're looking through the Oort Cloud, through the vertical dimensions we've explored tonight, through the hidden architecture of our solar system that extends equally above and below, everywhere and forever. Good night.